right, welcome back, everyone, to an introduction to artificial intelligence with Python. Now, so far in this class, we've used AI to solve a number of different problems, giving the AI instructions for how to search for a solution or how to satisfy certain constraints in order to find its way from some input point to some output point in order to solve some sort of problem. Today, we're going to turn to the world of learning, in particular the idea of machine learning, which generally refers to the idea where we are not going to give the computer explicit instructions for how to perform a task, but rather we are going to give the computer access to information in the form of data or patterns that it can learn from, and let the computer try and figure out what those patterns are, try and understand that data to be able to perform a task on its own. Now, machine learning comes in a number of different forms, and it's a very wide field. So today we'll explore some of the foundational algorithms and ideas that are behind a lot of the different areas within machine learning. And one of the most popular is the idea of supervised machine learning, or just supervised learning. And supervised learning is a particular type of task. It refers to the task where we give the computer access to a data set, where that data set consists of input-output pairs. And what we would like the computer to do is we would like our AI to be able to figure out some function that maps inputs to outputs. So we have a whole bunch of data that generally consists of some kind of input, some evidence, some information that the computer will have access to. And we would like the computer, based on that input information, to predict what some output is going to be. And we'll give it some data so that the computer can train its model on to begin to understand how it is that this information works and how it is that the inputs and outputs relate to each other. But ultimately, we hope that our computer will be able to figure out some function that, given those inputs, is able to get those outputs. There are a couple of different tasks within supervised learning. The one we'll focus on and start with is known as classification. And classification is the problem where if I give you a whole bunch of inputs, you need to figure out some way to map those inputs into discrete categories, where you can decide what those categories are. And it's the job of the computer to predict what those categories are going to be. So that might be, for example, I give you information about a banknote, like a US dollar, and I'm asking you to predict for me, does it belong to the category of authentic banknotes, or does it belong to the category of counterfeit banknotes? You need to categorize the input, and we want to train the computer to figure out some function to be able to do that calculation. Another example might be the case of weather, something we've talked about a little bit so far in this class, where we would like to predict on a given day, is it going to rain on that day? Is it going to be cloudy on that day? And before, we've seen how we could do this if we really give the computer all the exact probabilities for, if these are the conditions, what's the probability of rain? Oftentimes, we don't have access to that information, though. But what we do have access to is a whole bunch of data. So if we wanted to be able to predict something like, is it going to rain or is it not going to rain, we would give the computer historical information about days when it was raining and days when it was not raining, and ask the computer to look for patterns in that data. So what might that data look like? Well, we could structure that data in a table like this. This might be what our table looks like, where for any particular day, going back, we have information about that day's humidity, that day's air pressure, and then importantly, we have a label. Something where the human has said that on this particular day, it was raining or it was not raining. So you could fill in this table with a whole bunch of data. And what makes this what we would call a supervised learning exercise is that a human has gone in and labeled each of these data points, said that on this day, when these were the values for the humidity and pressure, that day was a rainy day, and this day was a not rainy day. And what we would like the computer to be able to do then is to be able to figure out, given these inputs, given the humidity and the pressure, can the computer predict what label should be associated with that day? Does that day look more like it's going to be a day that rains, or does it look more like a day when it's not going to rain? Put a little bit more mathematically, you can think of this as a function that takes two inputs, the inputs being the data points that our computer will have access to, things like humidity and pressure. So we could write a function f that takes as input both humidity and pressure. And then the output is going to be what category we would ascribe to these particular input points, what label we would associate with that input. So we've seen a couple of example data points here, where given this value for humidity and this value for pressure, we predict, is it going to rain or is it not going to rain? And that's information that we just gathered from the world. We measured on various different days what the humidity and pressure were. We observed whether or not we saw rain or no rain on that particular day. And this function f is what we would like to approximate. Now, the computer and we humans don't really know exactly how this function f works. It's probably quite a complex function. So what we're going to do instead is attempt to estimate it. We would like to come up with a hypothesis function, h, which is going to try to approximate what f does. We want to come up with some function h that will also take the same inputs and will also produce an output, rain or no rain. And ideally, we'd like these two functions to agree as much as possible. So the goal then of these supervised learning classification tasks is going to be to figure out, what does that function h look like? How can we begin to estimate, given all of this information, all of this data, what category or what label should be assigned to a particular data point? So where could you begin doing this? Well, a reasonable thing to do, especially in this situation, I have two numerical values, is I could try to plot this on a graph that has two axes, an x-axis and a y-axis. And in this case, we're just going to be using two numerical values as input. But these same types of ideas scale as you add more and more inputs as well. We'll be plotting things in 2 dimensions, but as we'll soon see, you could add more inputs and just imagine things in multiple dimensions. And while we humans have trouble conceptualizing anything really beyond 3 dimensions, at least visually, a computer has no problem with trying to imagine things in many, many more dimensions. That for a computer, each dimension is just some separate number that it is keeping track of. So it wouldn't be unreasonable for a computer to think in 10 dimensions or 100 dimensions to be able to try to solve a problem. But for now, we've got 2 inputs. So we'll graph things along 2 axes, an x-axis, which will here represent humidity, and a y-axis, which here represents pressure. And what we might do is say, let's take all of the days that were raining and just try to plot them on this graph and see where they fall on this graph. And here might be all of the rainy days, where each rainy day is one of these blue dots here that corresponds to a particular value for humidity and a particular value for pressure. And then I might do the same thing with the days that were not rainy. Say, take all the not rainy days, figure out what their values were for each of these 2 inputs, and go ahead and plot them on this graph as well. And I've here plotted them in red. So blue here stands for a rainy day. Red here stands for a not rainy day. And this then is the input, that my computer has access to all of this input. And what I would like the computer to be able to do is to train a model such that if I'm ever presented with a new input that doesn't have a label associated with it, something like this white dot here, I would like to predict, given those values for each of the 2 inputs, should we classify it as a blue dot, a rainy day, or should we classify it as a red dot, a not rainy day? And if you're just looking at this picture graphically, trying to say, all right, this white dot, does it look like it belongs to the blue category, or does it look like it belongs to the red category? I think most people would agree that it probably belongs to the blue category. And why is that? Well, it looks like it's close to other blue dots. And that's not a very formal notion, but it's a notion that we'll formalize in just a moment. That because it seems to be close to this blue dot here, like nothing else is closer to it, then we might say that it should be categorized as blue. It should fall into that category of, I think that day is going to be a rainy day based on that input. Might not be totally accurate, but it's a pretty good guess. And this type of algorithm is actually a very popular and common machine learning algorithm known as nearest neighbor classification. It's an algorithm for solving these classification type problems. And in nearest neighbor classification, it's going to perform this algorithm. What it'll do is, given an input, it will choose the class of the nearest data point to that input. By class, we just here mean category, like rain or no rain, counterfeit or not counterfeit. And we choose the category, or the class, based on the nearest data point. So given all that data, we just looked at, is the nearest data point a blue point or is it a red point? And depending on the answer to that question, we were able to make some sort of judgment. We were able to say something like, we think it's going to be blue, or we think it's going to be red. So likewise, we could apply this to other data points that we encounter as well. If suddenly this data point comes about, well, its nearest data is red. So we would go ahead and classify this as a red point, not raining. Things get a little bit trickier, though, when you look at a point like this white point over here, and you ask the same sort of question. Should it belong to the category of blue points, the rainy days, or should it belong to the category of red points, the not rainy days? Now, nearest neighbor classification would say the way you solve this problem is look at which point is nearest to that point. You look at this nearest point and say it's red. It's a not rainy day. And therefore, according to nearest neighbor classification, I would say that this unlabeled point, well, that should also be red. It should also be classified as a not rainy day. But your intuition might think that that's a reasonable judgment to make, that it's the closest thing is a not rainy day, so may as well guess that it's a not rainy day. But it's probably also reasonable to look at the bigger picture of things and to say, yes, it is true that the nearest point to it was a red point, but it's surrounded by a whole bunch of other blue points. So looking at the bigger picture, there's potentially an argument to be made that this point should actually be blue. And with only this data, we actually don't know for sure. We are given some input, something we're trying to predict, and we don't necessarily know what the output is going to be. So in this case, which one is correct is difficult to say. But oftentimes, considering more than just a single neighbor, considering multiple neighbors, can sometimes give us a better result. And so there's a variant on the nearest neighbor classification algorithm that is known as the K nearest neighbor classification algorithm, where K is some parameter, some number that we choose for how many neighbors are we going to look at. So one nearest neighbor classification is what we saw before. Just pick the one nearest neighbor and use that category. But with K nearest neighbor classification, where K might be 3 or 5 or 7, to say look at the 3 or 5 or 7 closest neighbors, closest data points to that point, works a little bit differently. This algorithm will give it an input, choose the most common class out of the K nearest data points to that input. So if we look at the 5 nearest points, and 3 of them say it's raining and 2 of them say it's not raining, we'll go with the 3 instead of the 2, because each one effectively gets one vote towards what they believe the category ought to be. And ultimately, you choose the category that has the most votes as a consequence of that. So K nearest neighbor classification, fairly straightforward one to understand intuitively. You just look at the neighbors and figure out what the answer might be. And it turns out this can work very, very well for solving a whole variety of different types of classification problems. But not every model is going to work under every situation. And so one of the things we'll take a look at today, especially in the context of supervised machine learning, is that there are a number of different approaches to machine learning, a number of different algorithms that we can apply, all solving the same type of problem, all solving some kind of classification problem where we want to take inputs and organize it into different categories. And no one algorithm is necessarily always going to be better than some other algorithm. They each have their trade-offs. And maybe depending on the data, one type of algorithm is going to be better suited to trying to model that information than some other algorithm. And so this is what a lot of machine learning research ends up being about, that when you're trying to apply machine learning techniques, you're often looking not just at one particular algorithm, but trying multiple different algorithms, trying to see what is going to give you the best results for trying to predict some function that maps inputs to outputs. So what then are the drawbacks of K nearest neighbor classification? Well, there are a couple. One might be that in a naive approach, at least, it could be fairly slow to have to go through and measure the distance between a point and every single one of these points that exists here. Now, there are ways of trying to get around that. There are data structures that can help to make it more quickly to be able to find these neighbors. There are also techniques you can use to try and prune some of this data, remove some of the data points so that you're only left with the relevant data points, just to make it a little bit easier. But ultimately, what we might like to do is come up with another way of trying to do this classification. And one way of trying to do the classification was looking at what are the neighboring points. But another way might be to try to look at all of the data and see if we can come up with some decision boundary, some boundary that will separate the rainy days from the not rainy days. And in the case of 2 dimensions, we can do that by drawing a line, for example. So what we might want to try to do is just find some line, find some separator that divides the rainy days, the blue points over here, from the not rainy days, the red points over there. We're now trying a different approach in contrast with the nearest neighbor approach, which just looked at local data around the input data point that we cared about. Now what we're doing is trying to use a technique known as linear regression to find some sort of line that will separate the 2 halves from each other. Now, sometimes it'll actually be possible to come up with some line that perfectly separates all the rainy days from the not rainy days. Realistically, though, this is probably cleaner than many data sets will actually be. Oftentimes, data is messier. There are outliers. There's random noise that happens inside of a particular system. And what we'd like to do is still be able to figure out what a line might look like. So in practice, the data will not always be linearly separable. Where linearly separable refers to some data set where I could draw a line just to separate the 2 halves of it perfectly. Instead, you might have a situation like this, where there's some rainy points that are on this side of the line and some not rainy points that are on that side of the line. And there may not be a line that perfectly separates half of the inputs from the other half, that perfectly separates all the rainy days from the not rainy days. But we can still say that this line does a pretty good job. And we'll try to formalize a little bit later what we mean when we say something like, this line does a pretty good job of trying to make that prediction. But for now, let's just say we're looking for a line that does as good of a job as we can at trying to separate one category of things from another category of things. So let's now try to formalize this a little bit more mathematically. We want to come up with some sort of function, some way we can define this line, And our inputs are things like humidity and pressure in this case. So our inputs we might call x1 is going to represent humidity, and x2 is going to represent pressure. These are our inputs that we are going to provide to our machine learning algorithm. And given those inputs, we would like for our model to be able to predict some sort of output. And we are going to predict that using our hypothesis function, which we called h. Our hypothesis function is going to take as input x1 and x2, humidity and pressure in this case. And you can imagine if we didn't just have 2 inputs, but we had 3 or 4 or 5 inputs or more, we could have this hypothesis function take all of those as input. And we'll see examples of that a little bit later as well. And now the question is, what does this hypothesis function do? Well, it really just needs to measure, like, is this data point on one side of the boundary, or is it on the other side of the boundary? And how do we formalize that boundary? Well, the boundary is generally going to be a linear combination of these input variables, at least in this particular case. So what we're trying to do when we say linear combination is take each of these inputs and multiply them by some number that we're going to have to figure out. We'll generally call that number a weight for how important should these variables be in trying to determine the answer. So we'll weight each of these variables with some weight. And we might add like a constant to it just to try and make the function a little bit different. And the result, we just need to compare. Like, is it greater than 0 or is it less than 0? To say, does it belong on one side of the line or the other side of the line? And so what that mathematical expression might look like is this. We would take each of my variables, x1 and x2, multiply them by some weight. I don't yet know what that weight is, but it's going to be some number, weight 1 and weight 2. And maybe we just want to add some other weight 0 to it, because the function might require us to shift the entire value up or down by a certain amount. And then we just compare. If we do all this math, is it greater than or equal to 0? If so, we might categorize that data point as a rainy day. And otherwise, we might say no rain. So the key here, then, is that this expression is how we are going to calculate whether it's a rainy day or not. We're going to do a bunch of math where we take each of the variables, multiply them by a weight, maybe add an extra weight to it, see if the result is greater than or equal to 0. And using that result of that expression, we're able to determine whether it's raining or not raining. This expression here is in this case going to refer to just some line. If you were to plot that graphically, it would just be some line. And what the line actually looks like depends upon these weights. x1 and x2 are the inputs, but these weights are really what determine the shape of that line, the slope of that line, and what that line actually looks like. So we then would like to figure out what these weights should be. We can choose whatever weights we want, but we want to choose weights in such a way that if you pass in a rainy day's humidity and pressure, then you end up with a result that is greater than or equal to 0. And we would like it such that if we passed into our hypothesis function a not rainy day's inputs, then the output that we get should be not raining. So before we get there, let's try and formalize this a little bit more mathematically, just to get a sense for how it is that you'll often see this if you ever go further into supervised machine learning and explore this idea. One thing is that generally for these categories, we'll sometimes just use the names of the categories, like rain and not rain. Often mathematically, if we're trying to do comparisons between these things, it's easier just to deal in the world of numbers. So we could just say 1 and 0, 1 for raining, 0 for not raining. So we do all this math, and if the result is greater than or equal to 0, we'll go ahead and say our hypothesis function outputs 1, meaning raining, and otherwise it outputs 0, meaning not raining. And oftentimes, this type of expression will instead express using vector mathematics. And all a vector is, if you're not familiar with the term, is it refers to a sequence of numerical values. You could represent that in Python using like a list of numerical values, or a tuple with numerical values. And here, we have a couple of sequences of numerical values. One of our vectors, one of our sequences of numerical values, are all of these individual weights, w0, w1, and w2. So we could construct what we'll call a weight vector, and we'll see why this is useful in a moment, called w, generally represented using a boldface w, that is just a sequence of these 3 weights, weight 0, weight 1, and weight 2. And to be able to calculate based on those weights whether we think a day is raining or not raining, we're going to multiply each of those weights by one of our input variables. That w2, this weight, is going to be multiplied by input variable x2. w1 is going to be multiplied by input variable x1. And w0 Well, it's not being multiplied by anything, but to make sure the vectors are the same length, and we'll see why that's useful in just a second, we'll just go ahead and say w0 is being multiplied by 1, because you can multiply by something by 1, and you end up getting the exact same number. So in addition to the weight vector w, we'll also have an input vector that we'll call x that has 3 values, 1, again, because we're just multiplying w0 by 1 eventually, and then x1 and x2. So here then we've represented 2 distinct vectors, a vector of weights that we need to somehow learn. The goal of our machine learning algorithm is to learn what this weight vector is supposed to be. We could choose any arbitrary set of numbers, and it would produce a function that tries to predict rain or not rain, but it probably wouldn't be very good. What we want to do is come up with a good choice of these weights so that we're able to do the accurate predictions. And then this input vector represents a particular input to the function, a data point for which we would like to estimate, is that day a rainy day, or is that day a not rainy day? And so that's going to vary just depending on what input is provided to our function, what it is that we are trying to estimate. And then to do the calculation, we want to calculate this expression here. And it turns out that expression is what we would call the dot product of these 2 vectors. The dot product of 2 vectors just means taking each of the terms in the vectors and multiplying them together. w0 multiplied by 1, w1 multiplied by x1, w2 multiplied by x2. And that's why these vectors need to be the same length. And then we just add all of the results together. So the dot product of w and x, our weight vector and our input vector, that's just going to be w0 times 1, or just w0, plus w1 times x1, multiplying these 2 terms together, plus w2 times x2, multiplying those terms together. So we have our weight vector, which we need to figure out. We need our machine learning algorithm to figure out what the weights should be. We have the input vector representing the data point that we're trying to predict a category for, predict a label for. And we're able to do that calculation by taking this dot product, which you'll often see represented in vector form. But if you haven't seen vectors before, you can think of it as identical to just this mathematical expression, just doing the multiplication, adding the results together, and then seeing whether the result is greater than or equal to 0 or not. This expression here is identical to the expression that we're calculating to see whether or not that answer is greater than or equal to 0 in this case. And so for that reason, you'll often see the hypothesis function written as something like this, a simpler representation where the hypothesis takes as input some input vector x, some humidity and pressure for some day, and we want to predict an output, like rain or no rain, or 1 or 0, if we choose to represent things numerically. And the way we do that is by taking the dot product of the weights and our input. If it's greater than or equal to 0, we'll go ahead and say the output is 1. Otherwise, the output is going to be 0. And this hypothesis, we say, is parameterized by the weights. Depending on what weights we choose, we'll end up getting a different hypothesis. If we choose the weights randomly, we're probably not going to get a very good hypothesis function. We'll get a 1 or a 0, but it's probably not accurately going to reflect whether we think a day is going to be rainy or not rainy. But if we choose the weights right, we can often do a pretty good job of trying to estimate whether we think the output of the function should be a 1 or a 0. And so the question then is how to figure out what these weights should be, how to be able to tune those parameters. And there are a number of ways you can do that. One of the most common is known as the perceptron learning rule. And we'll see more of this later. But the idea of the perceptron learning rule, and we're not going to get too deep into the mathematics, we'll mostly just introduce it more conceptually, is to say that given some data point that we would like to learn from, some data point that has an input x and an output y, where y is like 1 for rain or 0 for not rain, then we're going to update the weights. And we'll look at the formula in just a moment. But the big picture idea is that we can start with random weights, but then learn from the data. Like take the data points one at a time, and for each one of the data points, figure out, all right, what parameters do we need to change inside of the weights in order to better match that input point. And so that is the value of having access to a lot of data in the supervised machine learning algorithm, is that you take each of the data points and maybe look at them multiple times and constantly try and figure out whether you need to shift your weights in order to better create some weight vector that is able to correctly or more accurately try to estimate what the output should be, whether we think it's going to be raining or whether we think it's not going to be raining. So what does that weight update look like? Without going into too much of the mathematics, we're going to update each of the weights to be the result of the original weight plus some additional expression. And to understand this expression, y, well, y is what the actual output is. And hypothesis of x, the input, that's going to be what we thought the input was. And so I can replace this by saying like what the actual value was minus what our estimate was. And based on the difference between the actual value and what our estimate was, we might want to change our hypothesis, change the way that we do that estimation. If the actual value and the estimate were the same thing, meaning we were correctly able to predict what category this data point belonged to, well, then actual value minus estimate, that's just going to be 0, which means this whole term on the right-hand side goes to be 0, and the weight doesn't change. Weight I, where I is like weight 1 or weight 2 or weight 0, weight I just stays at weight I. And none of the weights change if we were able to correctly predict what category the input belonged to. But if our hypothesis didn't correctly predict what category the input belonged to, well, then maybe then we need to make some changes, adjust the weights so that we're better able to predict this kind of data point in the future. And what is the way we might do that? Well, if the actual value was bigger than the estimate, then, and for now we'll go ahead and assume that these x's are positive values, then if the actual value is bigger than the estimate, well, that means we need to increase the weight in order to make it such that the output is bigger, and therefore we're more likely to get to the right actual value. And so if the actual value is bigger than the estimate, then actual value minus estimate, that'll be a positive number. And so you imagine we're just adding some positive number to the weight just to increase it ever so slightly. And likewise, the inverse case is true, that if the actual value was less than the estimate, the actual value was 0, but we estimated 1, meaning it actually was not raining, but we predicted it was going to be raining, well, then we want to decrease the value of the weight, because then in that case we want to try and lower the total value of computing that dot product in order to make it less likely that we would predict that it would actually be raining. So no need to get too deep into the mathematics of that, but the general idea is that every time we encounter some data point, we can adjust these weights accordingly to try and make the weights better line up with the actual data that we have access to. And you can repeat this process with data point after data point until eventually, hopefully, your algorithm converges to some set of weights that do a pretty good job of trying to figure out whether a day is going to be rainy or not rainy. And just as a final point about this particular equation, this value alpha here is generally what we'll call the learning rate. It's just some parameter, some number we choose for how quickly we're actually going to be updating these weight values. So that if alpha is bigger, then we're going to update these weight values by a lot. And if alpha is smaller, then we'll update the weight values by less. And you can choose a value of alpha. Depending on the problem, different values might suit the situation better or worse than others. So after all of that, after we've done this training process of take all this data and using this learning rule, look at all the pieces of data and use each piece of data as an indication to us of do the weights stay the same? Do we increase the weights? Do we decrease the weights? And if so, by how much? What you end up with is effectively a threshold function. And we can look at what the threshold function looks like this. On the x-axis here, we have the output of that function, taking the weights, taking the dot product of it with the input. And on the y-axis, we have what the output is going to be. 0, which in this case represented like not raining, and 1, which in this case represented raining. And the way that our hypothesis function works is it calculates this value. And if it's greater than 0 or greater than some threshold value, then we declare that it's a rainy day. And otherwise, we declare that it's a not rainy day. And this then graphically is what that function looks like. That initially, when the value of this dot product is small, it's not raining, it's not raining, it's not raining. But as soon as it crosses that threshold, we suddenly say, OK, now it's raining, now it's raining, now it's raining. And the way to interpret this kind of representation is that anything on this side of the line, that would be the category of data points where we say, yes, it's raining. Anything that falls on this side of the line are the data points where we would say it's not raining. And again, we want to choose some value for the weights that results in a function that does a pretty good job of trying to do this estimation. But one tricky thing with this type of hard threshold is that it only leaves two possible outcomes. Right? We plug in some data as input, and the output we get is raining or not raining. And there's no room for anywhere in between. And maybe that's what you want. Maybe all you want is, given some data point, you would like to be able to classify it into 1 or 2 or more of these various different categories. But it might also be the case that you care about knowing how strong that prediction is, for example. So if we go back to this instance here, where we have rainy days on this side of the line, not rainy days on that side of the line, you might imagine that let's look now at these two white data points. This data point here that we would like to predict a label or a category for, and this data point over here that we would also like to predict a label or a category for. It seems likely that you could pretty confidently say that this data point, that should be a rainy day. Seems close to the other rainy days. If we're going by the nearest neighbor strategy, it's on this side of the line. If we're going by the strategy of just saying, which side of the line does it fall on, by figuring out what those weights should be. And if we're using the line strategy of just which side of the line does it fall on, which side of this decision boundary, well, we'd also say that this point here is also a rainy day, because it falls on the side of the line that corresponds to rainy days. But it's likely that even in this case, we would know that we don't feel nearly as confident about this data point on the left as compared to this data point on the right. That for this one on the right, we can feel very confident that, yes, it's a rainy day. This one, it's pretty close to the line if we're judging just by distance. And so you might be less sure. But our threshold function doesn't allow for a notion of less sure or more sure about something. It's what we would call a hard threshold. It's once you've crossed this line, then immediately we say, yes, this is going to be a rainy day. Anywhere before it, we're going to say it's not a rainy day. And that may not be helpful in a number of cases. One, this is not a particularly easy function to deal with. As you get deeper into the world of machine learning and are trying to do things like taking derivatives of these curves, this type of function makes things challenging. But the other challenge is that we don't really have any notion of gradation between things. We don't have a notion of, yes, this is a very strong belief that it's going to be raining, as opposed to, it's probably more likely than not that it's going to be raining, but maybe not totally sure about that either. So what we can do by taking advantage of a technique known as logistic regression is, instead of using this hard threshold type of function, we can use instead a logistic function, something we might call a soft threshold. And that's going to transform this into looking something a little more like this, something that more nicely curves. And as a result, the possible output values are no longer just 0 and 1, 0 for not raining, 1 for raining. But you can actually get any real numbered value between 0 and 1. That if you're way over on this side, then you get a value of 0. OK, it's not going to be raining, and we're pretty sure about that. And if you're over on this side, you get a value of 1. Like, yes, we're very sure that it's going to be raining. But in between, you could get some real numbered value, where a value like 0.7 might mean, we think it's going to rain. It's more probable that it's going to rain than not based on the data. But we're not as confident as some of the other data points might be. So one of the advantages of the soft threshold is that it allows us to have an output that could be some real number that potentially reflects some sort of probability, the likelihood that we think that this particular data point belongs to that particular category. And there are some other nice mathematical properties of that as well. So that then is two different approaches to trying to solve this type of classification problem. One is this nearest neighbor type of approach, where you just take a data point and look at the data points that are nearby to try and estimate what category we think it belongs to. And the other approach is the approach of saying, all right, let's just try and use linear regression, figure out what these weights should be, adjust the weights in order to figure out what line or what decision boundary is going to best separate these two categories. It turns out that another popular approach, a very popular approach if you just have a data set and you want to start trying to do some learning on it, is what we call the support vector machine. And we're not going to go too much into the mathematics of the support vector machine, but we'll at least explore it graphically to see what it is that it looks like. And the idea, or the motivation behind the support vector machine, is the idea that there are actually a lot of different lines that we could draw, a lot of different decision boundaries that we could draw to separate two groups. So if, for example, I had the red data points over here and the blue data points over here, one possible line I could draw is a line like this. That this line here would separate the red points from the blue points, and it does so perfectly. All the red points are on one side of the line. All the blue points are on the other side of the line. But this should probably make you a little bit nervous if you come up with a model and the model comes up with a line that looks like this. And the reason why is that you worry about how well it's going to generalize to other data points that are not necessarily in the data set that we have access to. For example, if there was a point that fell like right here, for example, on the right side of the line, well, then based on that, we might want to guess that it is, in fact, a red point, but it falls on the side of the line where instead we would estimate that it's a blue point instead. And so based on that, this line is probably not a great choice just because it is so close to these various data points. We might instead prefer like a diagonal line that just goes diagonally through the data set like we've seen before. But there too, there's a lot of diagonal lines that we could draw as well. For example, I could draw this diagonal line here, which also successfully separates all the red points from all of the blue points. From the perspective of something like just trying to figure out some setting of weights that allows us to predict the correct output, this line will predict the correct output for this particular set of data every single time, because the red points are on one side, the blue points are on the other. But yet again, you should probably be a little nervous because this line is so close to these red points, even though we're able to correctly predict on the input data. If there was a point that fell somewhere in this general area, our algorithm, this model, would say that, yeah, we think it's a blue point, when in actuality it might belong to the red category instead, just because it looks like it's close to the other red points. What we really want to be able to say, given this data, how can you generalize this as best as possible, is to come up with a line like this that seems like the intuitive line to draw. And the reason why it's intuitive is because it seems to be as far apart as possible from the red data and the blue data, so that if we generalize a little bit and assume that maybe we have some points that are different from the input but still slightly further away, we can still say that something on this side, probably red, something on that side, probably blue, and we can make those judgments that way. And that is what support vector machines are designed to do. They're designed to try and find what we call the maximum margin separator, where the maximum margin separator is just some boundary that maximizes the distance between the groups of points, rather than come up with some boundary that's very close to one set or the other, where in the case before we wouldn't have cared. As long as we're categorizing the input well, that seems all we need to do. The support vector machine will try and find this maximum margin separator, some way of trying to maximize that particular distance. And it does so by finding what we call the support vectors, which are the vectors that are closest to the line, and trying to maximize the distance between the line and those particular points. And it works that way in 2 dimensions. It also works in higher dimensions, where we're not looking for some line that separates the 2 data points, but instead looking for what we generally call a hyperplane, some decision boundary, effectively, that separates one set of data from the other set of data. And this ability of support vector machines to work in higher dimensions actually has a number of other applications as well. But one is that it helpfully deals with cases where data may not be linearly separable. So we talked about linear separability before, this idea that you can take data and just draw a line or some linear combination of the inputs that allows us to perfectly separate the 2 sets from each other. There are some data sets that are not linearly separable, and some where even too, you would not be able to find a good line at all that would try to do that kind of separation. Something like this, for example, where if you imagine here are the red points and the blue points surround it. If you try to find a line that divides the red points from the blue points, it's actually going to be difficult, if not impossible, to do. That any line you choose, well, if you draw a line here, then you've ignored all of these blue points that should actually be blue and not red. Anywhere else you draw a line, there's going to be a lot of error, a lot of mistakes, a lot of what we'll soon call loss to that line that you draw, a lot of points that you're going to categorize incorrectly. What we really want is to be able to find a better decision boundary that may not be just a straight line through this 2-dimensional space. And what support vector machines can do is they can begin to operate in higher dimensions and be able to find some other decision boundary, like this circle in this case, that actually is able to separate one of these sets of data from the other set of data a lot better. So oftentimes in data sets where the data is not linearly separable, support vector machines, by working in higher dimensions, can actually figure out a way to solve that kind of problem effectively. So that then, 3 different approaches to trying to solve these sorts of problems. We've seen support vector machines, and we've seen trying to use linear regression and the perceptron learning rule to be able to figure out how to categorize inputs and outputs. We've seen the nearest neighbor approach. No one necessarily better than any other again. It's going to depend on the data set, the information you have access to. It's going to depend on what the function looks like that you're ultimately trying to predict. And this is where a lot of research and experimentation can be involved in trying to figure out how it is to best perform that kind of estimation. But classification is only one of the tasks that you might encounter in supervised machine learning, because in classification, what we're trying to predict is some discrete category. We're trying to predict red or blue, rain or not rain, authentic or counterfeit. But sometimes what we want to predict is a real numbered value. And for that, we have a related problem, not classification, but instead known as regression. And regression is the supervised learning problem where we try and learn a function mapping inputs to outputs, same as before. But instead of the outputs being discrete categories, things like rain or not rain, in a regression problem, the output values are generally continuous values, some real number that we would like to predict. This happens all the time as well. You might imagine that a company might take this approach if it's trying to figure out, for instance, what the effect of its advertising is. Like, how do advertising dollars spent translate into sales for the company's product, for example? And so they might like to try to predict some function that takes as input the amount of money spent on advertising. And here we're just going to use one input. But again, you could scale this up to many more inputs as well if you have a lot of different kinds of data you have access to. And the goal is to learn a function that given this amount of spending on advertising, we're going to get this amount in sales. And you might judge based on having access to a whole bunch of data, like for every past month, here's how much we spent on advertising, and here is what sales were. And we would like to predict some sort of hypothesis function that, again, given the amount spent on advertising, can predict, in this case, some real number, some number estimate of how much sales we expect that company to do in this month or in this quarter or whatever unit of time we're choosing to measure things in. And so again, the approach to solving this type of problem, we could try using a linear regression type approach where we take this data and we just plot it. On the x-axis, we have advertising dollars spent. On the y-axis, we have sales. And we might just want to try and draw a line that does a pretty good job of trying to estimate this relationship between advertising and sales. And in this case, unlike before, we're not trying to separate the data points into discrete categories, but instead, in this case, we're just trying to find a line that approximates this relationship between advertising and sales, so that if we want to figure out what the estimated sales are for a particular advertising budget, you just look it up in this line, figure out for this amount of advertising, we would have this amount of sales, and just try and make the estimate that way. And so you can try and come up with a line, again, figuring out how to modify the weights using various different techniques to try and make it so that this line fits as well as possible. So with all of these approaches, then, to trying to solve machine learning style problems, the question becomes, how do we evaluate these approaches? How do we evaluate the various different hypotheses that we could come up with? Because each of these algorithms will give us some sort of hypothesis, some function that maps inputs to outputs. And we want to know how well does that function work. And you can think of evaluating these hypotheses and trying to get a better hypothesis as kind of like an optimization problem. In an optimization problem, if you recall from before, we were either trying to maximize some objective function by trying to find a global maximum, or we were trying to minimize some cost function by trying to find some global minimum. And in the case of evaluating these hypotheses, one thing we might say is that this cost function, the thing we're trying to minimize, we might be trying to minimize what we would call a loss function. And what a loss function is it is a function that is going to estimate for us how poorly our function performs. More formally, it's like a loss of utility. By whenever we predict something that is wrong, that is a loss of utility. That's going to add to the output of our loss function. And you could come up with any loss function that you want, just some mathematical way of estimating, given each of these data points, given what the actual output is, and given what our projected output is, our estimate, you could calculate some sort of numerical loss for it. But there are a couple of popular loss functions that are worth discussing, just so that you've seen them before. When it comes to discrete categories, things like rain or not rain, counterfeit or not counterfeit, one approach is the 0,1 loss function. And the way that works is for each of the data points, our loss function takes as input what the actual output is, like whether it was actually raining or not raining, and takes our prediction into account. Did we predict, given this data point, that it was raining or not raining? And if the actual value equals the prediction, well, then the 0,1 loss function will just say the loss is 0. There was no loss of utility because we were able to predict correctly. And otherwise, if the actual value was not the same thing as what we predicted, well, then in that case, our loss is 1. We lost something, lost some utility, because what we predicted was the output of the function was not what it actually was. And the goal then in a situation like this would be to come up with some hypothesis that minimizes the total empirical loss, the total amount that we've lost, if you add up for all these data points what the actual output is and what your hypothesis would have predicted. So in this case, for example, if we go back to classifying days as raining or not raining, and we came up with this decision boundary, how would we evaluate this decision boundary? How much better is it than drawing the line here or drawing the line there? Well, we could take each of the input data points, and each input data point has a label, whether it was raining or whether it was not raining. And we could compare it to the prediction, whether we predicted it would be raining or not raining, and assign it a numerical value as a result. So for example, these points over here, they were all rainy days, and we predicted they would be rainy because they fall on the bottom side of the line. So they have a loss of 0. Nothing lost from those situations. And likewise, same is true for some of these points over here, where it was not raining and we predicted it would not be raining either. Where we do have loss are points like this point here and that point there, where we predicted that it would not be raining, but in actuality, it's a blue point. It was raining. Or likewise here, we predicted that it would be raining, but in actuality, it's a red point. It was not raining. And so as a result, we miscategorized these data points that we were trying to train on. And as a result, there's some loss here. One loss here, there, here, and there, for a total loss of 4, for example, in this case. And that might be how we would estimate, or how we would say, that this line is better than a line that goes somewhere else, or a line that's further down, because this line might minimize the loss. So there's no way to do better than just these 4 points of loss if you're just drawing a straight line through our space. So the 0, 1 loss function checks. Did we get it right? Did we get it wrong? If we got it right, the loss is 0, nothing lost. If we got it wrong, then our loss function for that data point says 1. And we add up all of those losses across all of our data points to get some sort of empirical loss, how much we have lost across all of these original data points that our algorithm had access to. There are other forms of loss as well that work especially well when we deal with more real-valued cases, cases like the mapping between advertising budget and amount that we do in sales, for example. Because in that case, you care not just that you get the number exactly right, but you care how close you were to the actual value. If the actual value is you did like $2,800 in sales, and you predicted that you would do $2,900 in sales, maybe that's pretty good. That's much better than if you had predicted you'd do $1,000 in sales, for example. And so we would like our loss function to be able to take that into account as well. Take into account not just whether the actual value and the expected value are exactly the same, but also take into account how far apart they were. And so for that, one approach is what we call L1 loss. L1 loss doesn't just look at whether actual and predicted are equal to each other, but we take the absolute value of the actual value minus the predicted value. In other words, we just ask how far apart were the actual and predicted values, and we sum that up across all of the data points to be able to get what our answer ultimately is. So what might this actually look like for our data set? Well, if we go back to this representation, where we had advertising along the x-axis, sales along the y-axis, our line was our prediction, our estimate for any given amount of advertising, what we predicted sales was going to be. And our L1 loss is just how far apart vertically along the sales axis our prediction was from each of the data points. So we could figure out exactly how far apart our prediction was from each of the data points, and figure out, as a result of that, what our loss is overall for this particular hypothesis, just by adding up all of these various different individual losses for each of these data points. And our goal then is to try and minimize that loss, to try and come up with some line that minimizes what the utility loss is by judging how far away our estimate amount of sales is from the actual amount of sales. And turns out there are other loss functions as well. One that's quite popular is the L2 loss. The L2 loss, instead of just using the absolute value, like how far away the actual value is from the predicted value, it uses the square of actual minus predicted. So how far apart are the actual and predicted value, and it squares that value, effectively penalizing much more harshly anything that is a worse prediction. So you imagine if you have 2 data points that you predict as being 1 value away from their actual value, as opposed to 1 data point that you predict as being 2 away from its actual value. The L2 loss function will more harshly penalize that one that is 2 away, because it's going to square however much the difference is between the actual value and the predicted value. And depending on the situation, you might want to choose a loss function depending on what you care about minimizing. If you really care about minimizing the error on more outlier cases, then you might want to consider something like this. But if you've got a lot of outliers and you don't necessarily care about modeling them, then maybe an L1 loss function is preferable. But there are trade-offs here that you need to decide based on a particular set of data. But what you do run the risk of with any of these loss functions, with anything that we're trying to do, is a problem known as overfitting. And overfitting is a big problem that you can encounter in machine learning, which happens anytime a model fits too closely with a data set, and as a result fails to generalize. We would like our model to be able to accurately predict data and inputs and output pairs for the data that we have access to. But the reason we want it to do so is because we want our model to generalize well to data that we haven't seen before. I would like to take data from the past year of whether it was raining and not raining, and use that data to generalize it towards the future, to say in the future, is it going to be raining or not raining? Or if I have a whole bunch of data on what counterfeit and not counterfeit US dollar bills look like in the past when people have encountered them, I'd like to train a computer to be able to, in the future, generalize to other dollar bills that I might see as well. And the problem with overfitting is that if you try and tie yourself too closely to the data set that you're training your model on, you can end up not generalizing very well. So what does this look like? Well, we might imagine the rainy day and not rainy day example again from here, where the blue points indicate rainy days and the red points indicate not rainy days. And we decided that we felt pretty comfortable with drawing a line like this as the decision boundary between rainy days and not rainy days. So we can pretty comfortably say that points on this side more likely to be rainy days, points on that side more likely to be not rainy days. But the loss, the empirical loss, isn't 0 in this particular case, because we didn't categorize everything perfectly. There was this one outlier, this one day that it wasn't raining, but yet our model still predicts that it is raining. But that doesn't necessarily mean our model is bad. It just means the model isn't 100% accurate. If you really wanted to try and find a hypothesis that resulted in minimizing the loss, you could come up with a different decision boundary. It wouldn't be a line, but it would look something like this. Like this decision boundary does separate all of the red points from all of the blue points, because the red points fall on this side of this decision boundary, the blue points fall on the other side of the decision boundary. But this, we would probably argue, is not as good of a prediction, even though it seems to be more accurate based on all of the available training data that we have for training this machine learning model. We might say that it's probably not going to generalize well, that if there were other data points like here and there, we might still want to consider those to be rainy days, because we think this was probably just an outlier. So if the only thing you care about is minimizing the loss on the data you have available to you, you run the risk of overfitting. And this can happen in the classification case. It can also happen in the regression case, that here we predicted what we thought was a pretty good line relating advertising to sales, trying to predict what sales were going to be for a given amount of advertising. But I could come up with a line that does a better job of predicting the training data, and it would be something that looks like this, just connecting all of the various different data points. And now there's no loss at all. Now I've perfectly predicted, given any advertising, what sales are. And for all the data available to me, it's going to be accurate. But it's probably not going to generalize very well. I have overfit my model on the training data that is available to me. And so in general, we want to avoid overfitting. We'd like strategies to make sure that we haven't overfit our model to a particular data set. And there are a number of ways that you could try to do this. One way is by examining what it is that we're optimizing for. In an optimization problem, all we do is we say, there is some cost, and I want to minimize that cost. And so far, we've defined that cost function, the cost of a hypothesis, just as being equal to the empirical loss of that hypothesis. Like how far away are the actual data points, the outputs, away from what I predicted them to be based on that particular hypothesis. And if all you're trying to do is minimize cost, meaning minimizing the loss in this case, then the result is going to be that you might overfit. That to minimize cost, you're going to try and find a way to perfectly match all of the input data. And that might happen as a result of overfitting on that particular input data. So in order to address this, you could add something to the cost function. What counts as cost? Well, not just loss, but also some measure of the complexity of the hypothesis, where the complexity of the hypothesis is something that you would need to define for, how complicated does our line look? This is sort of an Occam's razor style approach where we want to give preference to a simpler decision boundary, like a straight line, for example, some simpler curve, as opposed to something far more complex that might represent the training data better, but might not generalize as well. We'll generally say that a simpler solution is probably the better solution and probably the one that is more likely to generalize well to other inputs. So we measure what the loss is, but we also measure the complexity. And now that all gets taken into account when we consider the overall cost. That yes, something might have less loss if it better predicts the training data, but if it's much more complex, it still might not be the best option that we have. And we need to come up with some balance between loss and complexity. And for that reason, you'll often see this represented as multiplying the complexity by some parameter that we have to choose, parameter lambda in this case, where we're saying, if lambda is a greater value, then we really want to penalize more complex hypotheses. Whereas if lambda is smaller, we're going to penalize more complex hypotheses a little bit. And it's up to the machine learning programmer to decide where they want to set that value of lambda. For how much do I want to penalize a more complex hypothesis that might fit the data a little better? And again, there's no one right answer to a lot of these things. That depending on the data set, depending on the data you have available to you and the problem you're trying to solve, your choice of these parameters may vary, and you may need to experiment a little bit to figure out what the right choice of that is ultimately going to be. This process, then, of considering not only loss, but also some measure of the complexity, is known as regularization. Regularization is the process of penalizing a hypothesis that is more complex in order to favor a simpler hypothesis that is more likely to generalize well, more likely to be able to apply to other situations that are dealing with other input points, unlike the ones that we've necessarily seen before. So oftentimes you'll see us add some regularizing term to what we're trying to minimize in order to avoid this problem of overfitting. Now, another way of making sure we don't overfit is to run some experiments and to see whether or not we are able to generalize our model that we've created to other data sets as well. And it's for that reason that oftentimes when you're doing a machine learning experiment, when you've got some data and you want to try and come up with some function that predicts, given some input, what the output is going to be, you don't necessarily want to do your training on all of the data you have available to you, that you could employ a method known as holdout cross-validation, where in holdout cross-validation, we split up our data. We split up our data into a training set and a testing set. The training set is the set of data that we're going to use to train our machine learning model. And the testing set is the set of data that we're going to use in order to test to see how well our machine learning model actually performed. So the learning happens on the training set. We figure out what the parameters should be. We figure out what the right model is. And then we see, all right, now that we've trained the model, see how well it does at predicting things inside of the testing set, some set of data that we haven't seen before. And the hope then is that we're going to be able to predict the testing set pretty well if we're able to generalize based on the training data that's available to us. If we've overfit the training data, though, and we're not able to generalize, well, then when we look at the testing set, it's likely going to be the case that we're not going to predict things in the testing set nearly as effectively. So this is one method of cross-validation, validating to make sure that the work we have done is actually going to generalize to other data sets as well. And there are other statistical techniques we can use as well. One of the downsides of this just holdout cross-validation is if you say I just split it 50-50. I train using 50% of the data and test using the other 50%, or you could choose other percentages as well, is that there's a fair amount of data that I am now not using to train, that I might be able to get a better model as a result, for example. So one approach is known as k-fold cross-validation. In k-fold cross-validation, rather than just divide things into two sets and run one experiment, we divide things into k different sets. So maybe I divide things up into 10 different sets and then run 10 different experiments. So if I split up my data into 10 different sets of data, then what I'll do is each time for each of my 10 experiments, I will hold out one of those sets of data, where I'll say, let me train my model on these 9 sets, and then test to see how well it predicts on set number 10. And then pick another set of 9 sets to train on, and then test it on the other one that I held out, where each time I train the model on everything minus the one set that I'm holding out, and then test to see how well our model performs on the test that I did hold out. And what you end up getting is like 10 different results, 10 different answers for how accurately our model worked. And oftentimes, you could just like take the average of those 10 to get an approximation for how well we think our model performs overall. But the key idea is separating the training data from the testing data, because you want to test your model on data that is different from what you trained the model on. Because the training, you want to avoid overfitting. You want to be able to generalize. And the way you test whether you're able to generalize is by looking at some data that you haven't seen before and seeing how well we're actually able to perform. And so if we want to actually implement any of these techniques inside of a programming language like Python, number of ways we could do that. We could write this from scratch on our own, but there are libraries out there that allow us to take advantage of existing implementations of these algorithms, that we can use the same types of algorithms in a lot of different situations. And so there's a library, very popular one, known as scikit-learn, which allows us in Python to be able to very quickly get set up with a lot of these different machine learning models. So this library has already written an algorithm for nearest neighbor classification, for doing perceptron learning, for doing a bunch of other types of inference and supervised learning that we haven't yet talked about. But using it, we can begin to try actually testing how these methods work and how accurately they perform. So let's go ahead and take a look at one approach to trying to solve this type of problem. All right, so I'm first going to pull up banknotes.csv, which is a whole bunch of data provided by UC Irvine, which is information about various different banknotes. So people took pictures of various different banknotes and measured various different properties of those banknotes. And in particular, some human categorized each of those banknotes as either a counterfeit banknote or as not counterfeit. And so what you're looking at here is each row represents one banknote. This is formatted as a CSV spreadsheet. We're just comma-separated values separating each of these various different fields. We have 4 different input values for each of these data points, just information, some measurement that was made on the banknote. And what those measurements exactly aren't as important as the fact that we do have access to this data. But more importantly, we have access for each of these data points to a label, where 0 indicates something like this was not a counterfeit bill, meaning it was an authentic bill, and a data point labeled 1 means that it is a counterfeit bill, at least according to the human researcher who labeled this particular data. So we have a whole bunch of data representing a whole bunch of different data points, each of which has these various different measurements that were made on that particular bill, and each of which has an output value, 0 or 1, 0 meaning it was a genuine bill, 1 meaning it was a counterfeit bill. And what we would like to do is use supervised learning to begin to predict or model some sort of function that can take these 4 values as input and predict what the output would be. We want our learning algorithm to find some sort of pattern that is able to predict, based on these measurements, something that you could measure just by taking a photo of a bill, predict whether that bill is authentic or whether that bill is counterfeit. And so how can we do that? Well, I'm first going to open up banknote0.py and see how it is that we do this. I'm first importing a lot of things from scikit-learn, but importantly, I'm going to set my model equal to the perceptron model, which is one of those models that we talked about before. We're just going to try and figure out some setting of weights that is able to divide our data into 2 different groups. Then I'm going to go ahead and read data in from my file, from banknotes.csv. And basically, for every row, I'm going to separate that row into the first 4 values of that row, which is the evidence for that row, and then the label, where if the final column in that row is a 0, the label is authentic, and otherwise it's going to be counterfeit. So I'm effectively reading data in from the CSV file, dividing it into a whole bunch of rows where each row has some evidence, those 4 input values that are going to be inputs to my hypothesis function, and then the label, the output, whether it is authentic or counterfeit. That is the thing that I am then trying to predict. So the next step is that I would like to split up my data set into a training set and a testing set. Some set of data that I would like to train my machine learning model on, and some set of data that I would like to use to test that model, see how well it performed. So what I'll do is I'll go ahead and figure out length of the data. How many data points do I have? I'll go ahead and take half of them, save that number as a number called holdout. That is how many items I'm going to hold out from my data set to save for the testing phase. I'll randomly shuffle the data so it's in some random order. And then I'll say my testing set will be all of the data up to the holdout. So I'll take holdout many data items, and that will be my testing set. My training data will be everything else, the information that I'm going to train my model on. And then I'll say I need to divide my training data into two different sets. I need to divide it into my x values, where x here represents the inputs. So the x values that I'm going to train on, are basically for every row in my training set, I'm going to get the evidence for that row, those 4 values, where it's basically a vector of 4 numbers, where that is going to be all of the input. And then I need the y values. What are the outputs that I want to learn from, the labels that belong to each of these various different input points? Well, that's going to be the same thing for each row in the training data. But this time, I take that row and get what its label is, whether it is authentic or counterfeit. So I end up with one list of all of these vectors of my input data, and one list which follows the same order, but is all of the labels that correspond with each of those vectors. And then to train my model, which in this case is just this perceptron model, I just call model.fit, pass in the training data and what the labels for those training data are, and scikit-learn will take care of fitting the model, will do the entire algorithm for me. And then when it's done, I can then test to see how well that model performed. So I can say, let me get all of these input vectors for what I want to test on. So for each row in my testing data set, go ahead and get the evidence. And the y values, those are what the actual values were for each of the rows in the testing data set, what the actual label is. But then I'm going to generate some predictions. I'm going to use this model and try and predict, based on the testing vectors, I want to predict what the output is. And my goal then is to now compare y testing with predictions. I want to see how well my predictions, based on the model, actually reflect what the y values were, what the output is that were actually labeled. Because I now have this labeled data, I can assess how well the algorithm worked. And so now I can just compute how well we did. I'm going to, this zip function basically just lets me look through 2 different lists, one by one at the same time. So for each actual value and for each predicted value, if the actual is the same thing as what I predicted, I'll go ahead and increment the counter by 1. Otherwise, I'll increment my incorrect counter by 1. And so at the end, I can print out, here are the results. Here's how many I got right. Here's how many I got wrong. And here was my overall accuracy, for example. So I can go ahead and run this. I can run python banknote0.py. And it's going to train on half the data set and then test on half the data set. And here are the results for my perceptron model. In this case, it correctly was able to classify 679 bills as correctly either authentic or counterfeit, and incorrectly classified 7 of them for an overall accuracy of close to 99% accurate. So on this particular data set, using this perceptron model, we were able to predict very well what the output was going to be. And we can try different models too. That scikit-learn makes it very easy just to swap out one model for another model. So instead of the perceptron model, I can use the support vector machine using the SVC, otherwise known as a support vector classifier, using a support vector machine to classify things into 2 different groups. And now see, all right, how well does this perform? And all right, this time, we were able to correctly predict 682 and incorrectly predicted 4 for accuracy of 99.4%. And we could even try the k neighbors classifier as the model instead. And this takes a parameter, n neighbors, for how many neighbors do you want to look at. Let's just look at one neighbor, the one nearest neighbor, and use that to predict. Go ahead and run this as well. And it looks like, based on the k neighbors classifier, looking at just one neighbor, we were able to correctly classify 685 data points, incorrectly classified 1. Maybe let's try 3 neighbors instead of just using one neighbor. Do more of a k nearest neighbors approach, where I look at the 3 nearest neighbors and see how that performs. And that one, in this case, seems to have gotten 100% of all of the predictions correctly described as either authentic banknotes or as counterfeit banknotes. And we could run these experiments multiple times, because I'm randomly reorganizing the data every time. We're technically training these on slightly different data sets. And so you might want to run multiple experiments to really see how well they're actually going to perform. But in short, they all perform very well. And while some of them perform slightly better than others here, that might not always be the case for every data set. But you can begin to test now by very quickly putting together these machine learning models using scikit-learn to be able to train on some training set and then test on some testing set as well. And this splitting up into training groups and testing happens so often that scikit-learn has functions built in for trying to do it. I did it all by hand just now. But if we take a look at banknotes 1, we take advantage of some other features that exist in scikit-learn. where we can really simplify a lot of our logic. That there is a function built into scikit-learn called train test split, which will automatically split data into a training group and a testing group. I just have to say what proportion should be in the testing group, something like 0.5, half the data, inside the testing group. Then I can fit the model on the training data, make the predictions on the testing data, and then just count up. And scikit-learn has some nice methods for just counting up how many times our testing data matched the predictions, how many times our testing data didn't match the predictions. So very quickly, you can write programs with not all that many lines of code. It's maybe like 40 lines of code to get through all of these predictions, and then as a result, see how well we're able to do. So these types of libraries can allow us, without really knowing the implementation details of these algorithms, to be able to use the algorithms in a very practical way to be able to solve these types of problems. So that then was supervised learning, this task of given a whole set of data, some input-output pairs, we would like to learn some function that maps those inputs to those outputs. But turns out there are other forms of learning as well. And another popular type of machine learning, especially nowadays, is known as reinforcement learning. And the idea of reinforcement learning is rather than just being given a whole data set at the beginning of input-output pairs, reinforcement learning is all about learning from experience. In reinforcement learning, our agent, whether it's like a physical robot that's trying to make actions in the world or just some virtual agent that is a program running somewhere, our agent is going to be given a set of rewards or punishments in the form of like numerical values, but you can think of them as reward or punishment. And based on that, it learns what actions to take in the future. That our agent, our AI, will be put in some sort of environment. It will make some actions, and based on the actions that it makes, it learns something. It either gets a reward when it does something well, it gets a punishment when it does something poorly, and it learns what to do or what not to do in the future based on those individual experiences. And so what this will often look like is it will often start with some agent, some AI, which might, again, be a physical robot if you're imagining a physical robot moving around, but it could also just be a program. And our agent is situated in their environment, where the environment is where they're going to make their actions, and it's what's going to give them rewards or punishments for various actions that they're in. So for example, the environment is going to start off by putting our agent inside of a state. Our agent has some state that in a game might be the state of the game that the agent is playing. In a world that the agent is exploring might be some position inside of a grid representing the world that they're exploring. But the agent is in some sort of state. And in that state, the agent needs to choose to take an action. The agent likely has multiple actions they can choose from, but they pick an action. So they take an action in a particular state. And as a result of that, the agent will generally get two things in response as we model them. The agent gets a new state that they find themselves in. After being in this state, taking one action, they end up in some other state. And they're also given some sort of numerical reward. Positive meaning reward, meaning it was a good thing. Negative, generally meaning they did something bad, they received some sort of punishment. And that is all the information the agent has. It's told what state it's in. It makes some sort of action. And based on that, it ends up in another state, and it ends up getting some particular reward. And it needs to learn, based on that information, what actions to begin to take in the future. And so you could imagine generalizing this to a lot of different situations. This is oftentimes how you train, if you've ever seen those robots that are now able to like walk around sort of the way humans do. It would be quite difficult to program the robot in exactly the right way to get it to walk the way humans do. You could instead train it through reinforcement learning. Give it some sort of numerical reward every time it does something good, like take steps forward, and punish it every time it does something bad, like fall over. And then let the AI just learn. Based on that sequence of rewards, based on trying to take various different actions, you can begin to have the agent learn what to do in the future and what not to do. So in order to begin to formalize this, the first thing we need to do is formalize this notion of what we mean about states and actions and rewards, like what does this world look like? And oftentimes we'll formulate this world as what's known as a Markov decision process. Similar in spirit to Markov chains, which you might recall from before. But a Markov decision process is a model that we can use for decision making, for an agent trying to make decisions in its environment. And it's a model that allows us to represent the various different states that an agent can be in, the various different actions that they can take, and also what the reward is for taking one action as opposed to another action. So what then does it actually look like? Well, if you recall a Markov chain from before, a Markov chain looked a little something like this, where we had a whole bunch of these individual states, and each state immediately transitioned to another state based on some probability distribution. We saw this in the context of the weather before, where if it was sunny, we said with some probability it'll be sunny the next day, with some other probability it'll be rainy, for example. But we could also imagine generalizing this. It's not just sun and rain anymore. We just have these states, where one state leads to another state according to some probability distribution. But in this original model, there was no agent that had any control over this process. It was just entirely probability-based, where with some probability we move to this next state, but maybe it's going to be some other state with some other probability. What we'll now have is the ability for the agent in this state to choose from a set of actions, where maybe instead of just one path forward, they have 3 different choices of actions that each lead down different paths. And even this is a bit of an oversimplification, because in each of these states, you might imagine more branching points where there are more decisions that can be taken as well. So we've extended the Markov chain to say that from a state, you now have available action choices. And each of those actions might be associated with its own probability distribution of going to various different states. Then in addition, we'll add another extension where anytime you move from a state, taking an action, going into this other state, we can associate a reward with that outcome, saying either R is positive, meaning some positive reward, or R is negative, meaning there was some sort of punishment. And this then is what we'll consider to be a Markov decision process. That a Markov decision process has some initial set of states, so states in the world that we can be in. We have some set of actions that, given a state, I can say, what are the actions that are available to me in that state, an action that I can choose from. Then we have some transition model. The transition model before just said that given my current state, what is the probability that I end up in that next state or this other state? The transition model now has effectively 2 things we're conditioning on. We're saying, given that I'm in this state and that I take this action, what's the probability that I end up in this next state? Now, maybe we live in a very deterministic world in this Markov decision process, where given a state and given an action, we know for sure what next state we'll end up in. But maybe there's some randomness in the world, that when you take in a state and you take an action, you might not always end up in the exact same state. There might be some probabilities involved there as well. The Markov decision process can handle both of those possible cases. And then finally, we have a reward function, generally called R, that in this case says, what is the reward for being in this state, taking this action, and then getting to S prime, this next state. So I'm in this original state, I take this action, I get to this next state. What is the reward for doing that process? And you can add up these rewards every time you take an action to get the total amount of rewards that an agent might get from interacting in a particular environment modeled using this Markov decision process. So what might this actually look like in practice? Well, let's just create a little simulated world here where I have this agent that is just trying to navigate its way. This agent is this yellow dot here, like a robot in the world, trying to navigate its way through this grid. And ultimately, it's trying to find its way to the goal. And if it gets to the green goal, then it's going to get some sort of reward. But then we might also have some red squares that are places where you get some sort of punishment, some bad place where we don't want the agent to go. And if it ends up in the red square, then our agent is going to get some sort of punishment as a result of that. But the agent originally doesn't know all of these details. It doesn't know that these states are associated with punishments, but maybe it does know that this state is associated with a reward. Maybe it doesn't. But it just needs to sort of interact with the environment to try and figure out what to do and what not to do. So the first thing the agent might do is, given no additional information, if it doesn't know what the punishments are, it doesn't know where the rewards are, it just might try and take an action. And it takes an action and ends up realizing that it got some sort of punishment. And so what does it learn from that experience? Well, it might learn that when you're in this state in the future, don't take the action move to the right, that is a bad action to take. That in the future, if you ever find yourself back in the state, don't take this action of going to the right when you're in this particular state, because that leads to punishment. That might be the intuition, at least. And so you could try doing other actions. You move up. All right, that didn't lead to any immediate rewards. Maybe try something else. Then maybe try something else. And all right, now you found that you got another punishment. And so you learn something from that experience. So the next time you do this whole process, you know that if you ever end up in this square, you shouldn't take the down action, because being in this state and taking that action ultimately leads to some sort of punishment, a negative reward, in other words. And this process repeats. That you might imagine just letting our agent explore the world, learning over time what states tend to correspond with poor actions, learning over time what states correspond with poor actions, until eventually, if it tries enough things randomly, it might find that eventually when you get to this state, if you take the up action in this state, it might find that you actually get a reward from that. And what it can learn from that is that if you're in this state, you should take the up action, because that leads to a reward. And over time, you can also learn that if you're in this state, you should take the left action, because that leads to this state that also lets you eventually get to the reward. So you begin to learn over time not only which actions are good in particular states, but also which actions are bad, such that once you know some sequence of good actions that leads you to some sort of reward, our agent can just follow those instructions, follow the experience that it has learned. We didn't tell the agent what the goal was. We didn't tell the agent where the punishments were. But the agent can begin to learn from this experience and learn to begin to perform these sorts of tasks better in the future. And so let's now try to formalize this idea, formalize the idea that we would like to be able to learn in this state, taking this action. Is that a good thing or a bad thing? There are lots of different models for reinforcement learning. We're just going to look at one of them today. And the one that we're going to look at is a method known as Q-learning. And what Q-learning is all about is it's about learning a function Q, that takes inputs s and a, where s is a state and a is an action that you take in that state. And what this Q function is going to do is it is going to estimate the value. How much reward will I get from taking this action in this state? Originally, we don't know what this Q function should be. But over time, based on experience, based on trying things out and seeing what the result is, I would like to try and learn what Q of SA is for any particular state and any particular action that I might take in that state. So what is the approach? Well, the approach originally is we'll start with QSA equal to 0 for all states S and for all actions A. That initially, before I've ever started anything, before I've had any experiences, I don't know the value of taking any action in any given state. So I'm going to assume that the value is just 0 all across the board. But then as I interact with the world, as I experience rewards or punishments, or maybe I go to a cell where I don't get either a reward or a punishment, I want to somehow update my estimate of QSA. I want to continually update my estimate of QSA based on the experiences and rewards and punishments that I've received, such that in the future, my knowledge of what actions are good in what states will be better. So when we take an action and receive some sort of reward, I want to estimate the new value of QSA. And I estimate that based on a couple of different things. I estimate it based on the reward that I'm getting from taking this action and getting into the next state. But assuming like the situation isn't over, assuming there are still future actions that I might take as well, I also need to take into account the expected future rewards. That if you imagine an agent interacting with the environment, and sometimes you'll take an action and get a reward, but then you can keep taking more actions and get more rewards, that these both are relevant, both the current reward I'm getting from this current step and also my future reward. And it might be the case that I'll want to take a step that doesn't immediately lead to a reward, because later on down the line, I know it will lead to more rewards as well. So there's a balancing act between current rewards that the agent experiences and future rewards that the agent experiences as well. And then we need to update QSA. So we estimate the value of QSA based on the current reward and the expected future rewards. And then we need to update this Q function to take into account this new estimate. Now, we already, as we go through this process, we'll already have an estimate for what we think the value is. Now we have a new estimate, and then somehow we need to combine these two estimates together. And we'll look at more formal ways that we can actually begin to do that. So to actually show you what this formula looks like, here is the approach we'll take with Q-learning. We're going to, again, start with Q of S and A being equal to 0 for all states. And then every time we take an action A in state S and observe a reward R, we're going to update our value, our estimate, for Q of SA. And the idea is that we're going to figure out what the new value estimate is minus what our existing value estimate is. So we have some preconceived notion for what the value is for taking this action in this state. Maybe our expectation is we currently think the value is 10. But then we're going to estimate what we now think it's going to be. Maybe the new value estimate is something like 20. So there's a delta of like 10 that our new value estimate is 10 points higher than what our current value estimate happens to be. And so we have a couple of options here. We need to decide how much we want to adjust our current expectation of what the value is of taking this action in this particular state, and what that difference is, how much we add or subtract from our existing notion of how much that we expect the value to be, is dependent on this parameter alpha, also called a learning rate. And alpha represents, in effect, how much we value new information compared to how much we value old information. An alpha value of 1 means we really value new information. That if we have a new estimate, then it doesn't matter what our old estimate is. We're only going to consider our new estimate because we always just want to take into consideration our new information. So the way that works is that if you imagine alpha being 1, well, then we're taking the old value of QSA and then adding 1 times the new value minus the old value, and that just leaves us with the new value. So when alpha is 1, all we take into consideration is what our new estimate happens to be. But over time, as we go through a lot of experiences, we already have some existing information. We might have tried taking this action 9 times already, and now we just tried it a 10th time. And we don't only want to consider this 10th experience. I also want to consider the fact that my prior 9 experiences, those were meaningful too. And that's data I don't necessarily want to lose. And so this alpha controls that decision, controls how important is the new information. 0 would mean ignore all the new information, just keep this Q value the same. 1 means replace the old information entirely with the new information. And somewhere in between, keep some sort of balance between these two values. We can put this equation a little bit more formally as well. The old value estimate is our old estimate for what the value is of taking this action in a particular state. That's just Q of S and A. So we have it once here, and we're going to add something to it. We're going to add alpha times the new value estimate minus the old value estimate. But the old value estimate we just look up by calling this Q function. And what then is the new value estimate? Based on this experience we have just taken, what is our new estimate for the value of taking this action in this particular state? Well, it's going to be composed of 2 parts. It's going to be composed of what reward did I just get from taking this action in this state? And then it's going to be, what can I expect my future rewards to be from this point forward? So it's going to be R, some reward I'm getting right now, plus whatever I estimate I'm going to get in the future. And how do I estimate what I'm going to get in the future? Well, it's a bit of another call to this Q function. It's going to be take the maximum across all possible actions I could take next and say, all right, of all of these possible actions I could take, which one is going to have the highest reward? So this then looks a little bit complicated. This is going to be our notion for how we're going to perform this kind of update. That I have some estimate, some old estimate for what the value is of taking this action in this state, and I'm going to update it based on new information. That I experience some reward, I predict what my future reward is going to be, and using that I update what I estimate the reward will be for taking this action in this particular state. And there are other additions you might make to this algorithm as well. Sometimes it might not be the case that future rewards you want to weight equally to current rewards. Maybe you want an agent that values like reward now over reward later. And so sometimes you can even add another term in here, some other parameter, where you discount future rewards and say future rewards are not as valuable as rewards immediately. That getting reward in the current time step is better than waiting a year and getting rewards later. But that's something up to the programmer to decide what that parameter ought to be. But the big picture idea of this entire formula is to say that every time we experience some new reward, we take that into account. We update our estimate of how good is this action. And then in the future, we can make decisions based on that algorithm. Once we have some good estimate for every state and for every action, what the value is of taking that action, then we can do something like implement a greedy decision-making policy. That if I am in a state and I want to know what action should I take in that state, well, then I consider, for all of my possible actions, what is the value of QSA? What is my estimated value of taking that action in that state? And I will just pick the action that has the highest value after I evaluate that expression. So I pick the action that has the highest value. And based on that, that tells me what action I should take. At any given state that I'm in, I can just greedily say, across all my actions, this action gives me the highest expected value. And so I'll go ahead and choose that action as the action that I take as well. But there is a downside to this kind of approach. And the downside comes up in a situation like this, where we know that there is some solution that gets me to the reward, and our agent has been able to figure that out. But it might not necessarily be the best way or the fastest way. If the agent is allowed to explore a little bit more, it might find that it can get the reward faster by taking some other route instead, by going through this particular path that is a faster way to get to that ultimate goal. And maybe we would like for the agent to be able to figure that out as well. But if the agent always takes the actions that it knows to be best, well, when it gets to this particular square, it doesn't know that this is a good action because it's never really tried it. But it knows that going down eventually leads its way to this reward. So it might learn in the future that it should just always take this route, and it's never going to explore and go along that route instead. So in reinforcement learning, there's this tension between exploration and exploitation. And exploitation generally refers to using knowledge that the AI already has. The AI already knows that this is a move that leads to reward, so we'll go ahead and use that move. And exploration is all about exploring other actions that we may not have explored as thoroughly before, because maybe one of these actions, even if I don't know anything about it, might lead to better rewards faster or to more rewards in the future. And so an agent that only ever exploits information and never explores might be able to get reward, but it might not maximize its rewards because it doesn't know what other possibilities are out there, possibilities that it would only know about by taking advantage of exploration. And so how can we try and address this? Well, one possible solution is known as the epsilon greedy algorithm, where we set epsilon equal to how often we want to just make a random move, where occasionally we will just make a random move in order to say, let's try to explore and see what happens. And then the logic of the algorithm will be, with probability 1 minus epsilon, choose the estimated best move. In a greedy case, we'd always choose the best move. But in epsilon greedy, we're most of the time going to choose the best move, or sometimes going to choose the best move. But sometimes, with probability epsilon, we're going to choose a random move instead. So every time we're faced with the ability to take an action, sometimes we're going to choose the best move. Sometimes we're just going to choose a random move. So this type of algorithm then can be quite powerful in a reinforcement learning context by not always just choosing the best possible move right now, but sometimes, especially early on, allowing yourself to make random moves that allow you to explore various different possible states and actions more. And maybe over time, you might decrease your value of epsilon, more and more often choosing the best move after you're more confident that you've explored what all of the possibilities actually are. So we can put this into practice, and one very common application of reinforcement learning is in game playing. That if you want to teach an agent how to play a game, you just let the agent play the game a whole bunch, and then the reward signal happens at the end of the game. When the game is over, if our AI won the game, it gets a reward of like 1, for example. And if it lost the game, it gets a reward of -1. And from that, it begins to learn what actions are good and what actions are bad. You don't have to tell the AI what's good and what's bad, but the AI figures it out based on that reward. Winning the game is some signal, losing the game is some signal, and based on all of that, it begins to figure out what decisions it should actually make. So one very simple game, which you may have played before, is a game called NIM. And in the game of NIM, you've got a whole bunch of objects in a whole bunch of different piles, where here I've represented each pile as an individual row. So you've got 1 object in the first pile, 3 in the second pile, 5 in the third pile, 7 in the fourth pile. And the game of NIM is a 2-player game where players take turns removing objects from piles. And the rule is that on any given turn, you are allowed to remove as many objects as you want from any one of these piles, any one of these rows. You have to remove at least 1 object, but you can remove as many as you want from exactly 1 of the piles. And whoever takes the last object loses. So player 1 might remove 4 from this pile here. Player 2 might remove 4 from this pile here. So now we've got 4 piles left, 1, 3, 1, and 3. Player 1 might remove the entirety of the second pile. Player 2, if they're being strategic, might remove 2 from the third pile. Now we've got 3 piles left, each with 1 object left. Player 1 might remove 1 from one pile. Player 2 removes 1 from the other pile. And now player 1 is left with choosing this 1 object from the last pile, at which point player 1 loses the game. So fairly simple game, piles of objects. Any turn you choose how many objects to remove from a pile. Whoever removes the last object loses. And this is the type of game you could encode into an AI fairly easily, because the states are really just 4 numbers. Every state is just how many objects in each of the 4 piles. And the actions are things like, how many am I going to remove from each one of these individual piles? And the reward happens at the end. That if you were the player that had to remove the last object, then you get some sort of punishment. But if you were not, and the other player had to remove the last object, well, then you get some sort of reward. So we could actually try and show a demonstration of this, that I've implemented an AI to play the game of Nim. All right, so here, what we're going to do is create an AI as a result of training the AI on some number of games that the AI is going to play against itself, where the idea is the AI will play games against itself, learn from each of those experiences, and learn what to do in the future. And then I, the human, will play against the AI. So initially, we'll say train 0 times, meaning we're not going to let the AI play any practice games against itself in order to learn from its experiences. We're just going to see how well it plays. And it looks like there are 4 piles. I can choose how many I remove from any one of the piles. So maybe from pile 3, I will remove 5 objects, for example. So now AI chose to take 1 item from pile 0. So I'm left with these piles now, for example. And so here I could choose maybe to say, I would like to remove from pile 2, I'll remove all 5 of them, for example. And so AI chose to take 2 away from pile 1. Now I'm left with 1 pile that has 1 object, 1 pile that has 2 objects. So from pile 3, I will remove 2 objects. And now I've left the AI with no choice but to take that last one. And so the game is over, and I was able to win. But I did so because the AI was really just playing randomly. It didn't have any prior experience that it was using in order to make these sorts of judgments. Now let the AI train itself on like 10,000 games. I'm going to let the AI play 10,000 games of Nim against itself. Every time it wins or loses, it's going to learn from that experience and learn in the future what to do and what not to do. So here then, I'll go ahead and run this again. And now you see the AI running through a whole bunch of training games, 10,000 training games against itself. And now it's going to let me make these sorts of decisions. So now I'm going to play against the AI. Maybe I'll remove 1 from pile 3. And the AI took everything from pile 3, so I'm left with 3 piles. I'll go ahead and from pile 2 maybe remove 3 items. And the AI removes 1 item from pile 0. I'm left with 2 piles, each of which has 2 items in it. I'll remove 1 from pile 1, I guess. And the AI took 2 from pile 2, leaving me with no choice but to take 1 away from pile 1. So it seems like after playing 10,000 games of Nim against itself, the AI has learned something about what states and what actions tend to be good, and has begun to learn some sort of pattern for how to predict what actions are going to be good and what actions are going to be bad in any given state. So reinforcement learning can be a very powerful technique for achieving these sorts of game-playing agents, agents that are able to play a game well just by learning from experience, whether that's playing against other people or by playing against itself and learning from those experiences as well. Now, Nim is a bit of an easy game to use reinforcement learning for because there are so few states. There are only states that are as many as how many different objects are in each of these various different piles. You might imagine that it's going to be harder if you think of a game like chess or games where there are many, many more states and many, many more actions that you can imagine taking, where it's not going to be as easy to learn for every state and for every action what the value is going to be. So oftentimes in that case, we can't necessarily learn exactly what the value is for every state and for every action, but we can approximate it. So much as we saw with minimax, so we could use a depth limiting approach to stop calculating at a certain point in time, we can do a similar type of approximation known as function approximation in a reinforcement learning context, where instead of learning a value of q for every state and every action, we just have some function that estimates what the value is for taking this action in this particular state that might be based on various different features of the state that the environment, that the agent happens to be in, where you might have to choose what those features actually are. But you can begin to learn some patterns that generalize beyond one specific state and one specific action, that you can begin to learn if certain features tend to be good things or bad things. Reinforcement learning can allow you, using a very similar mechanism, to generalize beyond one particular state and say, if this other state looks kind of like this state, then maybe the similar types of actions that worked in one state will also work in another state as well. And so this type of approach can be quite helpful as you begin to deal with reinforcement learning that exists in larger and larger state spaces where it's just not feasible to explore all of the possible states that could actually exist. So there then are two of the main categories of reinforcement learning: supervised learning, where you have labeled input and output pairs, and reinforcement learning, where an agent learns from rewards or punishments that it receives. The third major category of machine learning that we'll just touch on briefly is known as unsupervised learning. And unsupervised learning happens when we have data without any additional feedback, without labels. That in the supervised learning case, all of our data had labels. We labeled a data point with whether that was a rainy day or a not rainy day. And using those labels, we were able to infer what the pattern was. Or we labeled data as a counterfeit banknote or not a counterfeit. And using those labels, we were able to draw inferences and patterns to figure out what does a banknote look like versus not. In unsupervised learning, we don't have any access to any of those labels, but we still would like to learn some of those patterns. And one of the tasks that you might want to perform in unsupervised learning is something like clustering, where clustering is just a task of, given some set of objects, organize it into distinct clusters, groups of objects that are similar to one another. And there's lots of applications for clustering. It comes up in genetic research, where you might have a whole bunch of different genes, and you want to cluster them into similar genes if you're trying to analyze across a population or across species. It comes up in an image if you want to take all the pixels of an image, cluster them into different parts of the image. It comes a lot up in market research if you want to divide your consumers into different groups so you know which groups to target with certain types of product advertisements, for example, and a number of other contexts as well in which clustering can be very applicable. One technique for clustering is an algorithm known as k-means clustering. And what k-means clustering is going to do is it is going to divide all of our data points into k different clusters. And it's going to do so by repeating this process of assigning points to clusters and then moving around those clusters' centers. We're going to define a cluster by its center, the middle of the cluster, and then assign points to that cluster based on which center is closest to that point. And I'll show you an example of that now. Here, for example, I have a whole bunch of unlabeled data, just various data points that are in some sort of graphical space. And I would like to group them into various different clusters. But I don't know how to do that originally. And let's say I want to assign like 3 clusters to this group. And you have to choose how many clusters you want in k-means clustering, that you could try multiple and see how well those values perform. But I'll start just by randomly picking some places to put the centers of those clusters. So maybe I have a blue cluster, a red cluster, and a green cluster. And I'm going to start with the centers of those clusters just being in these 3 locations here. And what k-means clustering tells us to do is, once I have the centers of the clusters, assign every point to a cluster based on which cluster center it is closest to. So we end up with something like this, where all of these points are closer to the blue cluster center than any other cluster center. All of these points here are closer to the green cluster center than any other cluster center. And then these 2 points plus these points over here, those are all closest to the red cluster center instead. So here then is one possible assignment of all these points to 3 different clusters. But it's not great that it seems like in this red cluster, these points are kind of far apart. In this green cluster, these points are kind of far apart. It might not be my ideal choice of how I would cluster these various different data points. But k-means clustering is an iterative process, that after I do this, there's a next step, which is that after I've assigned all of the points to the cluster center that it is nearest to, we are going to recenter the clusters, meaning take the cluster centers, these diamond shapes here, and move them to the middle, or the average, effectively, of all of the points that are in that cluster. So we'll take this blue point, this blue center, and go ahead and move it to the middle, or to the center, of all of the points that were assigned to the blue cluster, moving it slightly to the right in this case. And we'll do the same thing for red. We'll move the cluster center to the middle of all of these points, weighted by how many points there are. There are more points over here, so the red center ends up moving a little bit further that way. And likewise for the green center, there are many more points on this side of the green center, so the green center ends up being pulled a little bit further in this direction. So we recenter all of the clusters, and then we repeat the process. We go ahead and now reassign all of the points to the cluster center that they are now closest to. And now that we've moved around the cluster centers, these cluster assignments might change. That this point originally was closer to the red cluster center, but now it's actually closer to the blue cluster center. Same goes for this point as well. And these 3 points that were originally closer to the green cluster center are now closer to the red cluster center instead. So we can reassign what colors or which clusters each of these data points belongs to, and then repeat the process again, moving each of these cluster means and the middles of the clusters to the mean, the average, of all of the other points that happen to be there, and repeat the process again. Go ahead and assign each of the points to the cluster that they are closest to. So once we reach a point where we've assigned all the points to clusters to the cluster that they are nearest to, and nothing changed, we've reached a sort of equilibrium in this situation, where no points are changing their allegiance. And as a result, we can declare this algorithm is now over. And we now have some assignment of each of these points into 3 different clusters. And it looks like we did a pretty good job of trying to identify which points are more similar to one another than they are to points in other groups. So we have the green cluster down here, this blue cluster here, and then this red cluster over there as well. And we did so without any access to some labels to tell us what these various different clusters were. We just used an algorithm in an unsupervised sense, without any of those labels, to figure out which points belonged to which categories. And again, lots of applications for this type of clustering technique. And there are many more algorithms in each of these various different fields within machine learning, supervised and reinforcement and unsupervised. But those are many of the big picture foundational ideas that underlie a lot of these techniques, where these are the problems that we're trying to solve. And we try and solve those problems using a number of different methods of trying to take data and learn patterns in that data, whether that's trying to find neighboring data points that are similar, or trying to minimize some sort of loss function, or any number of other techniques that allow us to begin to try to solve these sorts of problems. That then was a look at some of the principles that are at the foundation of modern machine learning, this ability to take data and learn from that data so that the computer can perform a task, even if they haven't explicitly been given instructions in order to do so. Next time, we'll continue this conversation about machine learning, looking at other techniques we can use for solving these sorts of problems. We'll see you then. All right, welcome back, everyone, to an introduction to artificial intelligence with Python. Now, last time we took a look at machine learning, a set of techniques that computers can use in order to take a set of data and learn some patterns inside of that data, learn how to perform a task, even if we, the programmers, didn't give the computer explicit instructions for how to perform that task. Today, we transition to one of the most popular techniques and tools within machine learning, that of neural networks. And neural networks were inspired as early as the 1940s by researchers who were thinking about how it is that humans learn, studying neuroscience in the human brain, and trying to see whether or not we could apply those same ideas to computers as well, and model computer learning off of human learning. So how is the brain structured? Well, very simply put, the brain consists of a whole bunch of neurons, and those neurons are connected to one another and communicate with one another in some way. In particular, if you think about the structure of a biological neural network, something like this, there are a couple of key properties that scientists observed. One was that these neurons are connected to each other and receive electrical signals from one another, that one neuron can propagate electrical signals to another neuron. And another point is that neurons process those input signals and then can be activated, that a neuron becomes activated at a certain point and then can propagate further signals onto neurons in the future. And so the question then became, could we take this biological idea of how it is that humans learn with brains and with neurons and apply that to a machine as well, in effect designing an artificial neural network, or an ANN, which will be a mathematical model for learning that is inspired by these biological neural networks. And what artificial neural networks will allow us to do is they will first be able to model some sort of mathematical function. Every time you look at a neural network, which we'll see more of later today, each one of them is really just some mathematical function that is mapping certain inputs to particular outputs based on the structure of the network, that depending on where we place particular units inside of this neural network, that's going to determine how it is that the network is going to function. And in particular, artificial neural networks are going to lend themselves to a way that we can learn what the network's parameters should be. We'll see more on that in just a moment. But in effect, we want a model such that it is easy for us to be able to write some code that allows for the network to be able to figure out how to model the right mathematical function given a particular set of input data. So in order to create our artificial neural network, instead of using biological neurons, we're just going to use what we're going to call units. Units inside of a neural network, which we can represent kind of like a node in a graph, which will here be represented just by a blue circle like this. And these artificial units, these artificial neurons, can be connected to one another. So here, for instance, we have two units that are connected by this edge inside of this graph, effectively. And so what we're going to do now is think of this idea as some sort of mapping from inputs to outputs. So we have one unit that is connected to another unit that we might think of this side as the input and that side as the output. And what we're trying to do then is to figure out how to solve a problem, how to model some sort of mathematical function. And this might take the form of something we saw last time, which was something like we have certain inputs, like variables x1 and x2. And given those inputs, we want to perform some sort of task, a task like predicting whether or not it's going to rain. And ideally, we'd like some way, given these inputs, x1 and x2, which stand for some sort of variables to do with the weather, we would like to be able to predict, in this case, a Boolean classification. Is it going to rain, or is it not going to rain? And we did this last time by way of a mathematical function. We defined some function, h, for our hypothesis function, that took as input x1 and x2, the two inputs that we cared about processing, in order to determine whether we thought it was going to rain or whether we thought it was not going to rain. The question then becomes, what does this hypothesis function do in order to make that determination? And we decided last time to use a linear combination of these input variables to determine what the output should be. So our hypothesis function was equal to something like this: weight 0 plus weight 1 times x1 plus weight 2 times x2. So what's going on here is that x1 and x2, those are input variables, the inputs to this hypothesis function. And each of those input variables is being multiplied by some weight, which is just some number. So x1 is being multiplied by weight 1. x2 is being multiplied by weight 2. And we have this additional weight, weight 0, that doesn't get multiplied by an input variable at all, that just serves to either move the function up or move the function's value down. You can think of this as either a weight that's just multiplied by some dummy value, like the number 1, and it's multiplied by 1, and so it's not multiplied by anything. Or sometimes you'll see in the literature, people call this variable weight 0 a bias, so that you can think of these variables as slightly different. We have weights that are multiplied by the input, and we separately add some bias to the result as well. You'll hear both of those terminologies used when people talk about neural networks and machine learning. So in effect, what we've done here is that in order to define a hypothesis function, we just need to decide and figure out what these weights should be to determine what values to multiply by our inputs to get some sort of result. Of course, at the end of this, what we need to do is make some sort of classification, like rainy or not rainy. And to do that, we use some sort of function that defines some sort of threshold. And so we saw, for instance, the step function, which is defined as 1 if the result of multiplying the weights by the inputs is at least 0, otherwise it's 0. And you can think of this line down the middle as kind of like a dotted line. Effectively, it stays at 0 all the way up to 1 point, and then the function steps or jumps up to 1. So it's 0 before it reaches some threshold, and then it's 1 after it reaches a particular threshold. And so this was one way we could define what we'll come to call an activation function, a function that determines when it is that this output becomes active, changes to a 1 instead of being a 0. But we also saw that if we didn't just want a purely binary classification, we didn't want purely 1 or 0, but we wanted to allow for some in-between real numbered values, we could use a different function. And there are a number of choices, but the one that we looked at was the logistic sigmoid function that has sort of an S-shaped curve, where we could represent this as a probability that maybe somewhere in between the probability of rain is something like 0.5. Maybe a little bit later, the probability of rain is 0.8. And so rather than just have a binary classification of 0 or 1, we could allow for numbers that are in between as well. And it turns out there are many other different types of activation functions, where an activation function just takes the output of multiplying the weights together and adding that bias, and then figuring out what the actual output should be. Another popular one is the rectified linear unit, otherwise known as ReLU. And the way that works is that it just takes its input and takes the maximum of that input and 0. So if it's positive, it remains unchanged. But if it's negative, it goes ahead and levels out at 0. And there are other activation functions that we could choose as well. But in short, each of these activation functions you can just think of as a function that gets applied to the result of all of this computation. We take some function g and apply it to the result of all of that calculation. And this then is what we saw last time, the way of defining some hypothesis function that takes in inputs, calculates some linear combination of those inputs, and then passes it through some sort of activation function to get our output. And this actually turns out to be the model for the simplest of neural networks, that we're going to instead represent this mathematical idea graphically by using a structure like this. Here then is a neural network that has two inputs. We can think of this as x1 and this is x2, and then one output, which you can think of as classifying whether or not we think it's going to rain or not rain, for example, in this particular instance. And so how exactly does this model work? Well, each of these two inputs represents one of our input variables, x1 and x2. And notice that these inputs are connected to this output via these edges, which are going to be defined by their weights. So these edges each have a weight associated with them, weight 1 and weight 2. And then this output unit, what it's going to do is it is going to calculate an output based on those inputs and based on those weights. This output unit is going to multiply all the inputs by their weights, add in this bias term, which you can think of as an extra W0 term that gets added into it, and then we pass it through an activation function. So this then is just a graphical way of representing the same idea we saw last time, just mathematically. And we're going to call this a very simple neural network. And we'd like for this neural network to be able to learn how to calculate some function. That we want some function for the neural network to learn. And the neural network is going to learn what should the values of W0, W1, and W2 be, what should the activation function be, in order to get the result that we would expect. So we can actually take a look at an example of this. What then is a very simple function that we might calculate? Well, if we recall back from when we were looking at propositional logic, one of the simplest functions we looked at was something like the OR function that takes two inputs, x and y, and outputs 1, otherwise known as true, if either one of the inputs or both of them are 1, and outputs a 0 if both of the inputs are 0 or false. So this then is the OR function. And this was the truth table for the OR function, that as long as either of the inputs are 1, the output of the function is 1. And the only case where the output is 0 is where both of the inputs are 0. So the question is, how could we take this and train a neural network to be able to learn this particular function? What would those weights look like? Well, we could do something like this. Here's our neural network. And I'll propose that in order to calculate the OR function, we're going to use a value of 1 for each of the weights. And we'll use a bias of -1. And then we'll just use this step function as our activation function. How then does this work? Well, if I wanted to calculate something like 0 or 0, which we know to be 0, because false or false is false, then what are we going to do? Well, our output unit is going to calculate this input multiplied by the weight. 0 times 1, that's 0. Same thing here. 0 times 1, that's 0. And we'll add to that the bias, -1. So that'll give us a result of -1. If we plot that on our activation function, -1 is here. It's before the threshold, which means either 0 or 1. It's only 1 after the threshold. Since -1 is before the threshold, the output that this unit provides is going to be 0. And that's what we would expect it to be, that 0 or 0 should be 0. What if instead we had had 1 or 0, where this is a number 1? Well, in this case, in order to calculate what the output is going to be, we again have to do this weighted sum. 1 times 1, that's 1. 0 times 1, that's 0. Sum of that so far is 1. Add -1 to that, well, then the output is 0. And if we plot 0 on this step function, 0 ends up being here. It's just at the threshold. And so the output here is going to be 1, because the output of 1 or 0, that's 1. So that's what we would expect as well. And just for one more example, if I had 1 or 1, what would the result be? Well, 1 times 1 is 1. 1 times 1 is 1. The sum of those is 2. I add the bias term to that. I get the number 1. 1 plotted on this graph is way over there. That's well beyond the threshold. And so this output is going to be 1 as well. The output is always 0 or 1, depending on whether or not we're past the threshold. And this neural network then models the OR function, a very simple function, definitely, but it still is able to model it correctly. If I give it the inputs, it will tell me what x1 or x2 happens to be. And you could imagine trying to do this for other functions as well. A function like the AND function, for instance, that takes two inputs and calculates whether both x and y are true. So if x is 1 and y is 1, then the output of x and y is 1. But in all of the other cases, the output is 0. How could we model that inside of a neural network as well? Well, it turns out we could do it in the same way, except instead of -1 as the bias, we can use -2 as the bias instead. What does that end up looking like? Well, if I had 1 and 1, that should be 1, because 1 true and true is equal to true. Well, I take 1 times 1, that's 1. 1 times 1 is 1. I get a total sum of 2 so far. Now I add the bias of -2, and I get the value 0. And 0, when I plot it on the activation function, is just past that threshold, and so the output is going to be 1. But if I add any other input, for example, like 1 and 0, well, the weighted sum of these is 1 plus 0 is going to be 1. -2 is going to give us -1. And -1 is not past that threshold, and so the output is going to be 0. So those then are some very simple functions that we can model using a neural network that has two inputs and one output, where our goal is to be able to figure out what those weights should be in order to determine what the output should be. And you could imagine generalizing this to calculate more complex functions as well, that maybe given the humidity and the pressure, we want to calculate what's the probability that it's going to rain, for example. Or we might want to do a regression style problem. We're given some amount of advertising, and given what month it is maybe, we want to predict what our expected sales are going to be for that particular month. So you could imagine these inputs and outputs being different as well. And it turns out that in some problems, we're not just going to have two inputs. And the nice thing about these neural networks is that we can compose multiple units together, make our networks more complex just by adding more units into this particular neural network. So the network we've been looking at has two inputs and one output. But we could just as easily say, let's go ahead and have 3 inputs in there, or have even more inputs, where we could arbitrarily decide however many inputs there are to our problem, all going to be calculating some sort of output that we care about figuring out the value of. How then does the math work for figuring out that output? Well, it's going to work in a very similar way. In the case of 2 inputs, we had 2 weights indicated by these edges, and we multiplied the weights by the numbers, adding this bias term. And we'll do the same thing in the other cases as well. If I have 3 inputs, you'll imagine multiplying each of these 3 inputs by each of these weights. If I had 5 inputs instead, we're going to do the same thing. Here I'm saying sum up from 1 to 5. xi multiplied by weight I. So take each of the 5 input variables, multiply them by their corresponding weight, and then add the bias to that. So this would be a case where there are 5 inputs into this neural network, for example. But there could be more, arbitrarily many nodes that we want inside of this neural network, where each time we're just going to sum up all of those input variables multiplied by their weight, and then add the bias term at the very end. And so this allows us to be able to represent problems that have even more inputs just by growing the size of our neural network. Now, the next question we might ask is a question about how it is that we train these neural networks. In the case of the OR function and the AND function, they were simple enough functions that I could just tell you, like, here are what the weights should be, and you could probably reason through it yourself, what the weights should be in order to calculate the output that you want. But in general, with functions like predicting sales or predicting whether or not it's going to rain, these are much trickier functions to be able to figure out. We would like the computer to have some mechanism of calculating what it is that the weights should be, how it is to set the weights, so that our neural network is able to accurately model the function that we care about trying to estimate. And it turns out that the strategy for doing this, inspired by the domain of calculus, is a technique called gradient descent. And what gradient descent is, it is an algorithm for minimizing loss when you're training a neural network. And recall that loss refers to how bad our hypothesis function happens to be, that we can define certain loss functions. And we saw some examples of loss functions last time that just give us a number for any particular hypothesis, saying how poorly does it model the data? How many examples does it get wrong? How are they worse or less bad as compared to other hypothesis functions that we might define? And this loss function is just a mathematical function. And when you have a mathematical function, in calculus what you could do is calculate something known as the gradient, which you can think of as like a slope. It's the direction the loss function is moving at any particular point. And what it's going to tell us is in which direction should we be moving these weights in order to minimize the amount of loss. And so generally speaking, we won't get into the calculus of it, but the high-level idea for gradient descent is going to look something like this. If we want to train a neural network, we'll go ahead and start just by choosing the weights randomly. Just pick random weights for all of the weights in the neural network. And then we'll use the input data that we have access to in order to train the network, in order to figure out what the weights should actually be. So we'll repeat this process again and again. The first step is we're going to calculate the gradient based on all of the data points. So we'll look at all the data and figure out what the gradient is at the place where we currently are for the current setting of the weights, which means in which direction should we move the weights in order to minimize the total amount of loss, in order to make our solution better. And once we've calculated that gradient, which direction we should move in the loss function, well, then we can just update those weights according to the gradient. Take a small step in the direction of those weights in order to try to make our solution a little bit better. And the size of the step that we take, that's going to vary, and you can choose that when you're training a particular neural network. But in short, the idea is going to be take all the data points, figure out based on those data points in what direction the weights should move, and then move the weights one small step in that direction. And if you repeat that process over and over again, adjusting the weights a little bit at a time based on all the data points, eventually you should end up with a pretty good solution to trying to solve this sort of problem. At least that's what we would hope to happen. Now, as you look at this algorithm, a good question to ask anytime you're analyzing an algorithm is, what is going to be the expensive part of doing the calculation? What's going to take a lot of work to try to figure out? What is going to be expensive to calculate? And in particular, in the case of gradient descent, the really expensive part is this all data points part right here. Having to take all of the data points and using all of those data points, figure out what the gradient is at this particular setting of all of the weights. Because odds are, in a big machine learning problem where you're trying to solve a big problem with a lot of data, you have a lot of data points in order to calculate. And figuring out the gradient based on all of those data points is going to be expensive. And you'll have to do it many times. You'll likely repeat this process again and again and again, going through all the data points, taking one small step over and over as you try and figure out what the optimal setting of those weights happens to be. It turns out that we would ideally like to be able to train our neural networks faster, to be able to more quickly converge to some sort of solution that is going to be a good solution to the problem. So in that case, there are alternatives to just standard gradient descent, which looks at all of the data points at once. We can employ a method like stochastic gradient descent, which will randomly just choose one data point at a time to calculate the gradient based on, instead of calculating it based on all of the data points. So the idea there is that we have some setting of the weights, we pick a data point, and based on that one data point, we figure out in which direction should we move all of the weights, and move the weights in that small direction. Then take another data point and do that again, and repeat this process again and again, maybe looking at each of the data points multiple times, but each time only using one data point to calculate the gradient, to calculate which direction we should move in. Now, just using one data point instead of all of the data points probably gives us a less accurate estimate of what the gradient actually is. But on the plus side, it's going to be much faster to be able to calculate, that we can much more quickly calculate what the gradient is based on one data point instead of calculating based on all of the data points and having to do all of that computational work again and again. So there are trade-offs here between looking at all of the data points and just looking at one data point. And it turns out that a middle ground that is also quite popular is a technique called mini-batch gradient descent, where the idea there is instead of looking at all of the data versus just a single point, we instead divide our data set up into small batches, groups of data points, where you can decide how big a particular batch is. But in short, you're just going to look at a small number of points at any given time, hopefully getting a more accurate estimate of the gradient, but also not requiring all of the computational effort needed to look at every single one of these data points. So gradient descent, then, is this technique that we can use in order to train these neural networks, in order to figure out what the setting of all of these weights should be if we want some way to try and get an accurate notion of how it is that this function should work, some way of modeling how to transform the inputs into particular outputs. Now, so far, the networks that we've taken a look at have all been structured similar to this. We have some number of inputs, maybe 2 or 3 or 5 or more, and then we have one output that is just predicting like rain or no rain, or just predicting one particular value. But often in machine learning problems, we don't just care about one output. We might care about an output that has multiple different values associated with it. So in the same way that we could take a neural network and add units to the input layer, we can likewise add input or add outputs to the output layer as well. Instead of just one output, you could imagine we have two outputs, or we could have like 4 outputs, for example, where in each case, as we add more inputs or add more outputs, if we want to keep this network fully connected between these two layers, we just need to add more weights. That now each of these input nodes has 4 weights associated with each of the 4 outputs. And that's true for each of these various different input nodes. So as we add nodes, we add more weights in order to make sure that each of the inputs can somehow be connected to each of the outputs so that each output value can be calculated based on what the value of the input happens to be. So what might a case be where we want multiple different output values? Well, you might consider that in the case of weather predicting, for example, we might not just care whether it's raining or not raining. There might be multiple different categories of weather that we would like to categorize the weather into. With just a single output variable, we can do a binary classification, like rain or no rain, for instance, 1 or 0. But it doesn't allow us to do much more than that. With multiple output variables, I might be able to use each one to predict something a little different. Maybe I want to categorize the weather into one of 4 different categories, something like is it going to be raining or sunny or cloudy or snowy? And I now have 4 output variables that can be used to represent maybe the probability that it is rainy as opposed to sunny, as opposed to cloudy, or as opposed to snowy. How then would this neural network work? Well, we have some input variables that represent some data that we have collected about the weather. Each of those inputs gets multiplied by each of these various different weights. So we have more multiplications to do, but these are fairly quick mathematical operations to perform. And then what we get is after passing them through some sort of activation function in the outputs, we end up getting some sort of number, where that number, you might imagine, you could interpret as like a probability that it is one category as opposed to another category. So here we're saying that based on the inputs, we think there is a 10% chance that it's raining, a 60% chance that it's sunny, a 20% chance that it's cloudy, a 10% chance that it's snowy. And given that output, if these represent like a probability distribution, well, then you could just pick whichever one has the highest value, in this case sunny, and say that, well, most likely, we think that this categorization of inputs means that the output should be snowy, or it should be sunny, and that is what we would expect the weather to be in this particular instance. And so this allows us to do these sort of multi-class classifications, where instead of just having a binary classification, 1 or 0, we can have as many different categories as we want, and we can have our neural network output these probabilities over which categories are more likely than other categories. And using that data, we're able to draw some sort of inference on what it is that we should do. So this was sort of the idea of supervised machine learning. I can give this neural network a whole bunch of data, a whole bunch of input data corresponding to some label, some output data, like we know that it was raining on this day, we know that it was sunny on that day. And using all of that data, the algorithm can use gradient descent to figure out what all of the weights should be in order to create some sort of model that hopefully allows us a way to predict what we think the weather is going to be. But neural networks have a lot of other applications as well. You could imagine applying the same sort of idea to a reinforcement learning sort of example as well, where you remember that in reinforcement learning, what we wanted to do is train some sort of agent to learn what action to take depending on what state they currently happen to be in. So depending on the current state of the world, we wanted the agent to pick from one of the available actions that is available to them. And you might model that by having each of these input variables represent some information about the state, some data about what state our agent is currently in. And then the output, for example, could be each of the various different actions that our agent could take, action 1, 2, 3, and 4. And you might imagine that this network would work in the same way, that based on these particular inputs, we go ahead and calculate values for each of these outputs. And those outputs could model which action is better than other actions. And we could just choose, based on looking at those outputs, which action we should take. And so these neural networks are very broadly applicable, that all they're really doing is modeling some mathematical function. So anything that we can frame as a mathematical function, something like classifying inputs into various different categories, or figuring out based on some input state what action we should take, these are all mathematical functions that we could attempt to model by taking advantage of this neural network structure, and in particular, taking advantage of this technique, gradient descent, that we can use in order to figure out what the weights should be in order to do this sort of calculation. Now, how is it that you would go about training a neural network that has multiple outputs instead of just one? Well, with just a single output, we could see what the output for that value should be, and then you update all of the weights that corresponded to it. And when we have multiple outputs, at least in this particular case, we can really think of this as 4 separate neural networks. That really we just have one network here that has these 3 inputs corresponding with these 3 weights corresponding to this one output value. And the same thing is true for this output value. This output value effectively defines yet another neural network that has these same 3 inputs, but a different set of weights that correspond to this output. And likewise, this output has its own set of weights as well, and same thing for the 4th output too. And so if you wanted to train a neural network that had 4 outputs instead of just 1, in this case, where the inputs are directly connected to the outputs, you could really think of this as just training 4 independent neural networks. We know what the outputs for each of these 4 should be based on our input data. And using that data, we can begin to figure out what all of these individual weights should be. And maybe there's an additional step at the end to make sure that we turn these values into a probability distribution such that we can interpret which one is better than another or more likely than another as a category or something like that. So this then seems like it does a pretty good job of taking inputs and trying to predict what outputs should be. And we'll see some real examples of this in just a moment as well. But it's important then to think about what the limitations of this sort of approach is, of just taking some linear combination of inputs and passing it into some sort of activation function. And it turns out that when we do this in the case of binary classification, of trying to predict, like, does it belong to one category or another, we can only predict things that are linearly separable. Because we're taking a linear combination of inputs and using that to define some decision boundary or threshold, then what we get is a situation where if we have this set of data, we can predict like a line that separates linearly the red points from the blue points. But a single unit that is making a binary classification, otherwise known as a perceptron, can't deal with a situation like this, where we've seen this type of situation before, where there is no straight line that just goes straight through the data that will divide the red points away from the blue points. It's a more complex decision boundary. The decision boundary somehow needs to capture the things inside of this circle, and there isn't really a line that will allow us to deal with that. So this is the limitation of the perceptron, these units that just make these binary decisions based on their inputs, that a single perceptron is only capable of learning a linearly separable decision boundary. All it can do is define a line. And sure, it can give us probabilities based on how close to that decision boundary we are, but it can only really decide based on a linear decision boundary. And so this doesn't seem like it's going to generalize well to situations where real-world data is involved, because real-world data often isn't linearly separable. It often isn't the case that we can just draw a line through the data and be able to divide it up into multiple groups. So what then is the solution to this? Well, what was proposed was the idea of a multi-layer neural network. That so far, all of the neural networks we've seen have had a set of inputs and a set of outputs, and the inputs are connected to those outputs. But in a multi-layer neural network, this is going to be an artificial neural network that has an input layer still, it has an output layer, but also has one or more hidden layers in between, other layers of artificial neurons or units that are going to calculate their own values as well. So instead of a neural network that looks like this, with 3 inputs and 1 output, you might imagine in the middle here injecting a hidden layer, something like this. This is a hidden layer that has 4 nodes. You could choose how many nodes or units end up going into the hidden layer. You can have multiple hidden layers as well. And so now each of these inputs isn't directly connected to the output. Each of the inputs is connected to this hidden layer. And then all of the nodes in the hidden layer, those are connected to the one output. And so this is just another step that we can take towards calculating more complex functions. Each of these hidden units will calculate its output value, otherwise known as its activation, based on a linear combination of all the inputs. And once we have values for all of these nodes, as opposed to this just being the output, we do the same thing again. Calculate the output for this node based on multiplying each of the values for these units by their weights as well. So in effect, the way this works is that we start with inputs. They get multiplied by weights in order to calculate values for the hidden nodes. Those get multiplied by weights in order to figure out what the ultimate output is going to be. And the advantage of layering things like this is it gives us an ability to model more complex functions. That instead of just having a single decision boundary, a single line dividing the red points from the blue points, each of these hidden nodes can learn a different decision boundary. And we can combine those decision boundaries to figure out what the ultimate output is going to be. And as we begin to imagine more complex situations, you could imagine each of these nodes learning some useful property or learning some useful feature of all of the inputs, and us somehow learning how to combine those features together in order to get the output that we actually want. Now, the natural question when we begin to look at this now is to ask the question of how do we train a neural network that has hidden layers inside of it? And this turns out to initially be a bit of a tricky question, because the input data that we are given is we are given values for all of the inputs, and we're given what the value of the output should be, what the category is, for example. But the input data doesn't tell us what the values for all of these nodes should be. So we don't know how far off each of these nodes actually is, because we're only given data for the inputs and the outputs. The reason this is called a hidden layer is because the data that is made available to us doesn't tell us what the values for all of these intermediate nodes should actually be. And so the strategy people came up with was to say that if you know what the error or the loss is on the output node, well, then based on what these weights are, if one of these weights is higher than another, you can calculate an estimate for how much the error from this node was due to this part of the hidden node, or this part of the hidden layer, or this part of the hidden layer, based on the values of these weights. In effect, saying that based on the error from the output, I can back propagate the error and figure out an estimate for what the error is for each of these nodes in the hidden layer as well. And there's some more calculus here that we won't get into the details of, but the idea of this algorithm is known as back propagation. It's an algorithm for training a neural network with multiple different hidden layers. And the idea for this, the pseudocode for it, will again be if we want to run gradient descent with back propagation, we'll start with a random choice of weights, as we did before. And now we'll go ahead and repeat the training process again and again. But what we're going to do each time is now we're going to calculate the error for the output layer first. We know the output and what it should be, and we know what we calculated, so we can figure out what the error there is. But then we're going to repeat for every layer, starting with the output layer, moving back into the hidden layer, then the hidden layer before that, if there are multiple hidden layers, going back all the way to the very first hidden layer, assuming there are multiple. We're going to propagate the error back one layer. Whatever the error was from the output, figure out what the error should be a layer before that based on what the values of those weights are. And then we can update those weights. So graphically, the way you might think about this is that we first start with the output. We know what the output should be. We know what output we calculated. And based on that, we can figure out, all right, how do we need to update those weights, back propagating the error to these nodes. And using that, we can figure out how we should update these weights. And you might imagine if there are multiple layers, we could repeat this process again and again to begin to figure out how all of these weights should be updated. And this backpropagation algorithm is really the key algorithm that makes neural networks possible. It makes it possible to take these multi-level structures and be able to train those structures depending on what the values of these weights are in order to figure out how it is that we should go about updating those weights in order to create some function that is able to minimize the total amount of loss, to figure out some good setting of the weights that will take the inputs and translate it into the output that we expect. And this works, as we said, not just for a single hidden layer, but you can imagine multiple hidden layers, where each hidden layer, we just define however many nodes we want, where each of the nodes in one layer, we can connect to the nodes in the next layer, defining more and more complex networks that are able to model more and more complex types of functions. And so this type of network is what we might call a deep neural network, part of a larger family of deep learning algorithms, if you've ever heard that term. And all deep learning is about is it's using multiple layers to be able to predict and be able to model higher level features inside of the input, to be able to figure out what the output should be. And so a deep neural network is just a neural network that has multiple of these hidden layers, where we start at the input, calculate values for this layer, then this layer, then this layer, and then ultimately get an output. And this allows us to be able to model more and more sophisticated types of functions, that each of these layers can calculate something a little bit different, and we can combine that information to figure out what the output should be. Of course, as with any situation of machine learning, as we begin to make our models more and more complex, to model more and more complex functions, the risk we run is something like overfitting. And we talked about overfitting last time in the context of overfitting based on when we were training our models to be able to learn some sort of decision boundary, where overfitting happens when we fit too closely to the training data. And as a result, we don't generalize well to other situations as well. And one of the risks we run with a far more complex neural network that has many, many different nodes is that we might overfit based on the input data. We might grow over-reliant on certain nodes to calculate things just purely based on the input data that doesn't allow us to generalize very well to the output. And there are a number of strategies for dealing with overfitting. But one of the most popular in the context of neural networks is a technique known as dropout. And what dropout does is when we're training the neural network, what we'll do in dropout is temporarily remove units, temporarily remove these artificial neurons from our network, chosen at random. And the goal here is to prevent over-reliance on certain units. So what generally happens in overfitting is that we begin to over-rely on certain units inside the neural network to be able to tell us how to interpret the input data. What dropout will do is randomly remove some of these units in order to reduce the chance that we over-rely on certain units to make our neural network more robust, to be able to handle the situations even when we just drop out particular neurons entirely. So the way that might work is we have a network like this, and as we're training it, when we go about trying to update the weights the first time, we'll just randomly pick some percentage of the nodes to drop out of the network. It's as if those nodes aren't there at all. It's as if the weights associated with those nodes aren't there at all, and we'll train it this way. Then the next time we update the weights, we'll pick a different set and just go ahead and train that way. And then again, randomly choose and train with other nodes that have been dropped out as well. And the goal of that is that after the training process, if you train by dropping out random nodes inside of this neural network, you hopefully end up with a network that's a little bit more robust, that doesn't rely too heavily on any one particular node, but more generally learns how to approximate a function in general. So that then is a look at some of these techniques that we can use in order to implement a neural network, to get at the idea of taking this input, passing it through these various different layers in order to produce some sort of output. And what we'd like to do now is take those ideas and put them into code. And to do that, there are a number of different machine learning libraries, neural network libraries that we can use that allow us to get access to someone's implementation of backpropagation and all of these hidden layers. And one of the most popular, developed by Google, is known as TensorFlow, a library that we can use for quickly creating neural networks and modeling them and running them on some sample data to see what the output is going to be. And before we actually start writing code, we'll go ahead and take a look at TensorFlow's playground, which will be an opportunity for us just to play around with this idea of neural networks in different layers, just to get a sense for what it is that we can do by taking advantage of neural networks. So let's go ahead and go into TensorFlow's playground, which you can go to by visiting that URL from before. And what we're going to do now is we're going to try and learn the decision boundary for this particular output. I want to learn to separate the orange points from the blue points. And I'd like to learn some sort of setting of weights inside of a neural network that will be able to separate those from each other. The features we have access to, our input data, are the x value and the y value, so the two values along each of the two axes. And what I'll do now is I can set particular parameters, like what activation function I would like to use. And I'll just go ahead and press play and see what happens. And what happens here is that you'll see that just by using these two input features, the x value and the y value, with no hidden layers, just take the input, x and y values, and figure out what the decision boundary is, our neural network learns pretty quickly that in order to divide these 2 points, we should just use this line. This line acts as a decision boundary that separates this group of points from that group of points, and it does it very well. You can see up here what the loss is. The training loss is 0, meaning we were able to perfectly model separating these 2 points from each other inside of our training data. So this was a fairly simple case of trying to apply a neural network. Because the data is very clean, it's very nicely linearly separable, we could just draw a line that separates all of those points from each other. Let's now consider a more complex case. So I'll go ahead and pause the simulation, and we'll go ahead and look at this data set here. This data set is a little bit more complex now. In this data set, we still have blue and orange points that we'd like to separate from each other. But there's no single line that we can draw that is going to be able to figure out how to separate the blue from the orange, because the blue is located in these 2 quadrants and the orange is located here and here. It's a more complex function to be able to learn. So let's see what happens if we just try and predict, based on those inputs, the x and y coordinates, what the output should be. I'll press play. And what you'll notice is that we're not really able to draw much of a conclusion, that we're not able to very cleanly see how we should divide the orange points from the blue points. And you don't see a very clean separation there. So it seems like we don't have enough sophistication inside of our network to be able to model something that is that complex. We need a better model for this neural network. And I'll do that by adding a hidden layer. So now I have a hidden layer that has 2 neurons inside of it. So I have 2 inputs that then go to 2 neurons inside of a hidden layer that then go to our output. And now I'll press play. And what you'll notice here is that we're able to do slightly better. We're able to now say, all right, these points are definitely blue. These points are definitely orange. We're still struggling a little bit with these points up here, though. And what we can do is we can see for each of these hidden neurons, what is it exactly that these hidden neurons are doing? Each hidden neuron is learning its own decision boundary. And we can see what that boundary is. This first neuron is learning, all right, this line that seems to separate some of the blue points from the rest of the points. This other hidden neuron is learning another line that seems to be separating the orange points in the lower right from the rest of the points. So that's why we're able to sort of figure out these 2 areas in the bottom region. But we're still not able to perfectly classify all of the points. So let's go ahead and add another neuron. Now we've got 3 neurons inside of our hidden layer, and see what we're able to learn now. All right, well, now we seem to be doing a better job. By learning 3 different decision boundaries, which each of the 3 neurons inside of our hidden layer, we're able to much better figure out how to separate these blue points from the orange points. And you can see what each of these hidden neurons is learning. Each one is learning a slightly different decision boundary. And then we're combining those decision boundaries together to figure out what the overall output should be. And maybe we can try it one more time by adding a 4th neuron there and try learning that. And it seems like now we can do even better at trying to separate the blue points from the orange points. But we were only able to do this by adding a hidden layer, by adding some layer that is learning some other boundaries and combining those boundaries to determine the output. And the strength, the size and thickness of these lines indicate how high these weights are, how important each of these inputs is for making this sort of calculation. And we can do maybe one more simulation. Let's go ahead and try this on a data set that looks like this. Go ahead and get rid of the hidden layer. Here now we're trying to separate the blue points from the orange points, where all the blue points are located, again, inside of a circle effectively. So we're not going to be able to learn a line. Notice I press play, and we're really not able to draw any sort of classification at all, because there is no line that cleanly separates the blue points from the orange points. So let's try to solve this by introducing a hidden layer. I'll go ahead and press play. And all right, with 2 neurons in a hidden layer, we're able to do a little better, because we effectively learn 2 different decision boundaries. We learn this line here, and we learn this line on the right-hand side. And right now we're just saying, all right, well, if it's in between, we'll call it blue, and if it's outside, we'll call it orange. So not great, but certainly better than before, that we're learning one decision boundary and another. And based on those, we can figure out what the output should be. But let's now go ahead and add a 3rd neuron and see what happens now. I go ahead and train it. And now, using 3 different decision boundaries that are learned by each of these hidden neurons, we're able to much more accurately model this distinction between blue points and orange points. We're able to figure out, maybe with these 3 decision boundaries, combining them together, you can imagine figuring out what the output should be and how to make that sort of classification. And so the goal here is just to get a sense for having more neurons in these hidden layers allows us to learn more structure in the data, allows us to figure out what the relevant and important decision boundaries are. And then using this backpropagation algorithm, we're able to figure out what the values of these weights should be in order to train this network to be able to classify one category of points away from another category of points instead. And this is ultimately what we're going to be trying to do whenever we're training a neural network. So let's go ahead and actually see an example of this. You'll recall from last time that we had this banknotes file that included information about counterfeit banknotes as opposed to authentic banknotes, where I had like 4 different values for each banknote, and then a categorization of whether that banknote is considered to be authentic or a counterfeit note. And what I wanted to do was, based on that input information, figure out some function that could calculate, based on the input information, what category it belonged to. And what I've written here in banknotes.py is a neural network that will learn just that, a network that learns, based on all of the input, whether or not we should categorize a banknote as authentic or as counterfeit. The first step is the same as what we saw from last time. I'm really just reading the data in and getting it into an appropriate format. And so this is where more of the writing Python code on your own comes in terms of manipulating this data, massaging the data into a format that will be understood by a machine learning library like scikit-learn or like TensorFlow. And so here I separate it into a training and a testing set. And now what I'm doing down below is I'm creating a neural network. Here I'm using TF, which stands for TensorFlow. Up above, I said import TensorFlow as TF. TF just an abbreviation that we'll often use, so we don't need to write out TensorFlow every time we want to use anything inside of the library. I'm using tf.keras. Keras is an API, a set of functions that we can use in order to manipulate neural networks inside of TensorFlow. And it turns out there are other machine learning libraries that also use the Keras API. But here I'm saying, all right, go ahead and give me a model that is a sequential model, a sequential neural network, meaning one layer after another. And now I'm going to add to that model what layers I want inside of my neural network. So here I'm saying model.add. Go ahead and add a dense layer. And when we say a dense layer, we mean a layer that is just each of the nodes inside of the layer is going to be connected to each of the nodes from the previous layer. So we have a densely connected layer. This layer is going to have 8 units inside of it. So it's going to be a hidden layer inside of our neural network with 8 different units, 8 artificial neurons, each of which might learn something different. And I just sort of chose 8 arbitrarily. You could choose a different number of hidden nodes inside of the layer. And as we saw before, depending on the number of units there are inside of your hidden layer, more units means you can learn more complex functions. So maybe you can more accurately model the training data. But it comes at the cost. More units means more weights that you need to figure out how to update, so it might be more expensive to do that calculation. And you also run the risk of overfitting on the data. If you have too many units and you learn to just overfit on the training data, that's not good either. So there is a balance, and there's often a testing process where you'll train on some data and maybe validate how well you're doing on a separate set of data, often called a validation set, to see, all right, which setting of parameters, how many layers should I have, how many units should be in each layer, which one of those performs the best on the validation set. So you can do some testing to figure out what these hyperparameters, so-called, should be equal to. Next, I specify what the input shape is, meaning, all right, what does my input look like? My input has 4 values, and so the input shape is just 4, because we have 4 inputs. And then I specify what the activation function is. And the activation function, again, we can choose. There are a number of different activation functions. Here I'm using relu, which you might recall from earlier. And then I'll add an output layer. So I have my hidden layer. Now I'm adding one more layer that will just have 1 unit, because all I want to do is predict something like counterfeit bill or authentic bill. So I just need a single unit. And the activation function I'm going to use here is that sigmoid activation function, which again was that S-shaped curve that just gave us like a probability of what is the probability that this is a counterfeit bill as opposed to an authentic bill. So that then is the structure of my neural network, a sequential neural network that has 1 hidden layer with 8 units inside of it, and then 1 output layer that just has a single unit inside of it. And I can choose how many units there are. I can choose the activation function. Then I'm going to compile this model. TensorFlow gives you a choice of how you would like to optimize the weights. There are various different algorithms for doing that. What type of loss function you want to use. Again, many different options for doing that. And then how I want to evaluate my model. Well, I care about accuracy. I care about like how many of my points am I able to classify correctly versus not correctly as counterfeit or not counterfeit. And I would like it to report to me how accurate my model is performing. Then, now that I've defined that model, I call model.fit to say go ahead and train the model. Train it on all the training data plus all of the training labels, so labels for each of those pieces of training data. And I'm saying run it for 20 epochs, meaning go ahead and go through each of these training points 20 times, effectively. Go through the data 20 times and keep trying to update the weights. If I did it for more, I could train for even longer and maybe get a more accurate result. But then after I've fitted on all the data, I'll go ahead and just test it. I'll evaluate my model using model.evaluate built into TensorFlow that is just going to tell me how well do I perform on the testing data. So ultimately, this is just going to give me some numbers that tell me how well we did in this particular case. So now what I'm going to do is go into banknotes and go ahead and run banknotes.py. And what's going to happen now is it's going to read in all of that training data. It's going to generate a neural network with my inputs, my 8 hidden layers, or 8 hidden units inside my layer, and then an output unit. And now what it's doing is it's training. It's training 20 times. And each time you can see how my accuracy is increasing on my training data. It starts off the very first time not very accurate, though better than random, something like 79% of the time, it's able to accurately classify one bill from another. But as I keep training, notice this accuracy value improves and improves and improves until after I've trained through all the data points 20 times, it looks like my accuracy is above 99% on the training data. And here's where I tested it on a whole bunch of testing data. And it looks like in this case, I was also like 99.8% accurate. So just using that, I was able to generate a neural network that can detect counterfeit bills from authentic bills based on this input data 99.8% of the time, at least based on this particular testing data. And I might want to test it with more data as well, just to be confident about that. But this is really the value of using a machine learning library like TensorFlow. And there are others available for Python and other languages as well, that all I have to do is define the structure of the network and define the data that I'm going to pass into the network. And then TensorFlow runs the backpropagation algorithm for learning what all of those weights should be, for figuring out how to train this neural network to be able to accurately as possible, figure out what the output values should be there as well. And so this then was a look at what it is that neural networks can do just using these sequences of layer after layer after layer. And you can begin to imagine applying these to much more general problems. And one big problem in computing and artificial intelligence more generally is the problem of computer vision. Computer vision is all about computational methods for analyzing and understanding images. You might have pictures that you want the computer to figure out how to deal with, how to process those images, and figure out how to produce some sort of useful result out of this. You've seen this in the context of social media websites that are able to look at a photo that contains a whole bunch of faces, and it's able to figure out what's a picture of whom, and label those and tag them with appropriate people. This is becoming increasingly relevant as we begin to discuss self-driving cars. These cars now have cameras, and we would like for the computer to have some sort of algorithm that looks at the image and figures out like what color is the light, what cars are around us and in what direction, for example. And so computer vision is all about like taking an image and figuring out what sort of computation, what sort of calculation we can do with that image. It's also relevant in the context of something like handwriting recognition. This, what you're looking at, is an example of the MNIST dataset. It's a big dataset just of handwritten digits that we could use to ideally try and figure out how to predict, given someone's handwriting, given a photo of a digit that they have drawn, can you predict whether it's a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, for example? So this sort of handwriting recognition is yet another task that we might want to use computer vision tasks and tools to be able to apply it towards. This might be a task that we might care about. So how then can we use neural networks to be able to solve a problem like this? Well, neural networks rely upon some sort of input, where that input is just numerical data. We have a whole bunch of units where each one of them just represents some sort of number. And so in the context of something like handwriting recognition, or in the context of just an image, you might imagine that an image is really just a grid of pixels, grid of dots where each dot has some sort of color. And in the context of something like handwriting recognition, you might imagine that if you just fill in each of these dots in a particular way, you can generate like a 2 or an 8, for example, based on which dots happen to be shaded in and which dots are not. And we can represent each of these pixel values just using numbers. So for a particular pixel, for example, 0 might represent entirely black. Depending on how you're representing color, it's often common to represent color values on a 0 to 255 range, so that you can represent a color using 8 bits for a particular value, like how much white is in the image. So 0 might represent all black. 255 might represent entirely white as a pixel, and somewhere in between might represent some shade of gray, for example. But you might imagine not just having a single slider that determines how much white is in the image, but if you had a color image, you might imagine 3 different numerical values, a red, green, and blue value, where the red value controls how much red is in the image. We have one value for controlling how much green is in the pixel, and one value for how much blue is in the pixel as well. And depending on how it is that you set these values of red, green, and blue, you can get a different color. And so any pixel can really be represented, in this case, by 3 numerical values, a red value, a green value, and a blue value. And if you take a whole bunch of these pixels, assemble them together inside of a grid of pixels, then you really just have a whole bunch of numerical values that you can use in order to perform some sort of prediction task. And so what you might imagine doing is using the same techniques we talked about before, just design a neural network with a lot of inputs. that for each of the pixels, we might have 1 or 3 different inputs in the case of a color image, a different input that is just connected to a deep neural network, for example. And this deep neural network might take all of the pixels inside of the image of like what digit a person drew, and the output might be like 10 neurons that classify it as a 0 or a 1 or a 2 or a 3, or just tells us in some way what that digit happens to be. Now, there are a couple of drawbacks to this approach. The first drawback to the approach is just the size of this input array, that we have a whole bunch of inputs. If we have a big image that has a lot of different channels, we're looking at a lot of inputs and therefore a lot of weights that we have to calculate. And a second problem is the fact that by flattening everything into just this structure of all the pixels, we've lost access to a lot of the information about the structure of the image that's relevant. That really, when a person looks at an image, they're looking at particular features of that image. They're looking at curves. They're looking at shapes. They're looking at what things can you identify in different regions of the image and maybe put those things together in order to get a better picture of what the overall image is about. And by just turning it into pixel values for each of the pixels, sure, you might be able to learn that structure, but it might be challenging in order to do so. It might be helpful to take advantage of the fact that you can use properties of the image itself, the fact that it's structured in a particular way, to be able to improve the way that we learn based on that image too. So in order to figure out how we can train our neural networks to better be able to deal with images, we'll introduce a couple of ideas, a couple of algorithms that we can apply that allow us to take the image and extract some useful information out of that image. And the first idea we'll introduce is the notion of image convolution. And what image convolution is all about is it's about filtering an image, sort of extracting useful or relevant features out of the image. And the way we do that is by applying a particular filter that basically adds the value for every pixel with the values for all of the neighboring pixels to it, according to some sort of kernel matrix, which we'll see in a moment, is going to allow us to weight these pixels in various different ways. And the goal of image convolution, then, is to extract some sort of interesting or useful features out of an image, to be able to take a pixel and, based on its neighboring pixels, maybe predict some sort of valuable information. Something like taking a pixel and looking at its neighboring pixels, you might be able to predict whether or not there's some sort of curve inside the image, or whether it's forming the outline of a particular line or a shape, for example. And that might be useful if you're trying to use all of these various different features to combine them to say something meaningful about an image as a whole. So how then does image convolution work? Well, we start with a kernel matrix. And the kernel matrix looks something like this. And the idea of this is that given a pixel, that will be the middle pixel, we're going to multiply each of the neighboring pixels by these values in order to get some sort of result by summing up all the numbers together. So if I take this kernel, which you can think of as like a filter that I'm going to apply to the image, and let's say that I take this image. This is a 4x4 image. We'll think of it as just a black and white image where each one is just a single pixel value. So somewhere between 0 and 255, for example. So we have a whole bunch of individual pixel values like this. And what I'd like to do is apply this kernel, this filter, so to speak, to this image. And the way I'll do that is, all right, the kernel is 3x3. You can imagine a 5x5 kernel or a larger kernel too. And I'll take it and just first apply it to the first 3x3 section of the image. And what I'll do is I'll take each of these pixel values, multiply it by its corresponding value in the filter matrix, and add all of the results together. So here, for example, I'll say 10 times 0 plus 20 times -1 plus 30 times 0, so on and so forth, doing all of this calculation. And at the end, if I take all of these values, multiply them by their corresponding value in the kernel, add the results together, for this particular set of 9 pixels, I get the value of 10, for example. And then what I'll do is I'll slide this 3x3 grid effectively over, slide the kernel by 1 to look at the next 3x3 section. And here I'm just sliding it over by 1 pixel, but you might imagine a different stride length where maybe I jump by multiple pixels at a time if you really wanted to. You have different options here. But here I'm just sliding over, looking at the next 3x3 section, and I'll do the same math. 20 times 0 plus 30 times -1 plus 40 times 0 plus 20 times -1, so on and so forth, plus 30 times 5. And what I end up getting is the number 20. Then you can imagine shifting over to this one, doing the same thing, calculating like the number 40, for example, and then doing the same thing here and calculating a value there as well. And so what we have now is what we'll call like a feature map. We have taken this kernel, applied it to each of these various different regions, and what we get is some representation of like a filtered version of that image. And so to give a more concrete example of why it is that this kind of thing could be useful, let's take this kernel matrix, for example, which is quite a famous one, that has an 8 in the middle, and then all of the neighboring pixels get a -1. And let's imagine we wanted to apply that to a 3x3 part of an image that looks like this, where all of the values are the same. They're all 20, for instance. Well, in this case, if you do 20 times 8, and then subtract 20, subtract 20, subtract 20 for each of the 8 neighbors, well, the result of that is you just get that expression, which comes out to be 0. You multiplied 20 by 8, but then you subtracted 20 8 times, according to that particular kernel. The result of all of that is just 0. So the takeaway here is that when a lot of the pixels are the same value, we end up getting a value close to 0. If, though, we had something like this, 20s along this first row, then 50s in the second row, and 50s in the third row, well, then when you do this same kind of math, 20 times -1, 20 times -1, so on and so forth, then I get a higher value, a value like 90 in this particular case. And so the more general idea here is that by applying this kernel, -1s, 8 in the middle, and then -1s, what I get is when this middle value is very different from the neighboring values, like 50 is greater than these 20s, then you'll end up with a value higher than 0. Like if this number is higher than its neighbors, you end up getting a bigger output. But if this value is the same as all of its neighbors, then you get a lower output, something like 0. And it turns out that this sort of filter can therefore be used in something like detecting edges in an image. If I want to detect like the boundaries between various different objects inside of an image, I might use a filter like this, which is able to tell whether the value of this pixel is different from the values of the neighboring pixels, if it's like greater than the values of the pixels that happen to surround it. And so we can use this in terms of image filtering. And so I'll show you an example of that. I have here in filter.py a file that uses Python's image library, or PIL, to do some image filtering. I go ahead and open an image, and then all I'm going to do is apply a kernel to that image. It's going to be a 3x3 kernel, same kind of kernel we saw before. And here is the kernel. This is just a list representation of the same matrix that I showed you a moment ago. It's -1, -1, -1. The second row is -1, 8, -1. And the third row is all -1s. And then at the end, I'm going to go ahead and show the filtered image. So if, for example, I go into convolution directory, and I open up an image like bridge.png, this is what an input image might look like, just an image of a bridge over a river. Now I'm going to go ahead and run this filter program on the bridge. And what I get is this image here. Just by taking the original image and applying that filter to each 3x3 grid, I've extracted all of the boundaries, all of the edges inside the image that separate one part of the image from another. So here I've got a representation of boundaries between particular parts of the image. And you might imagine that if a machine learning algorithm is trying to learn like what an image is of, a filter like this could be pretty useful. That maybe the machine learning algorithm doesn't care about all of the details of the image. It just cares about certain useful features. It cares about particular shapes that are able to help it determine that based on the image, this is going to be a bridge, for example. And so this type of idea of image convolution can allow us to apply filters to images that allow us to extract useful results out of those images, taking an image and extracting its edges, for example. And you might imagine many other filters that could be applied to an image that are able to extract particular values as well. And a filter might have separate kernels for the red values, the green values, and the blue values that are all summed together at the end, such that you could have particular filters looking for, is there red in this part of the image? Are there green in other parts of the image? You can begin to assemble these relevant and useful filters that are able to do these calculations as well. So that then was the idea of image convolution, applying some sort of filter to an image to be able to extract some useful features out of that image. But all the while, these images are still pretty big. Like there's a lot of pixels involved in the image. And realistically speaking, if you've got a really big image, that poses a couple of problems. One, it means a lot of input going into the neural network. But two, it also means that we really have to care about what's in each particular pixel. Whereas realistically, we often, like if you're looking at an image, you don't care whether something is in one particular pixel versus the pixel immediately to the right of it. They're pretty close together. You really just care about whether there's a particular feature in some region of the image. And maybe you don't care about exactly which pixel it happens to be in. And so there's a technique we can use known as pooling. And what pooling is it means reducing the size of an input by sampling from regions inside of the input. So we're going to take a big image and turn it into a smaller image by using pooling. And in particular, one of the most popular types of pooling is called max pooling. And what max pooling does is it pools just by choosing the maximum value in a particular region. So for example, let's imagine I had this 4x4 image, but I wanted to reduce its dimensions. I wanted to make it a smaller image so that I have fewer inputs to work with. Well, what I could do is I could apply a 2x2 max pool, where the idea would be that I'm going to first look at this 2x2 region and say, what is the maximum value in that region? Well, it's the number 50, so we'll go ahead and just use the number 50. And then we'll look at this 2x2 region. What is the maximum value here? It's 110, so that's going to be my value. Likewise here, the maximum value looks like 20. Go ahead and put that there. Then for this last region, the maximum value is 40, so we'll go ahead and use that. And what I have now is a smaller representation of this same original image that I obtained just by picking the maximum value from each of these regions. So again, the advantages here are now I only have to deal with a 2x2 input instead of a 4x4. And you could imagine shrinking the size of an image even more. But in addition to that, I'm now able to make my analysis independent of whether a particular value was in this pixel or this pixel. Like, I don't care if the 50 was here or here. As long as it was generally in this region, I'll still get access to that value. So it makes our algorithms a little bit more robust as well. So that then is pooling, taking the size of the image, reducing it a little bit by just sampling from particular regions inside of the image. And now we can put all of these ideas together, pooling, image convolution, and neural networks all together into another type of neural network called a convolutional neural network, or a CNN, which is a neural network that uses this convolution step, usually in the context of analyzing an image, for example. And so the way that a convolutional neural network works is that we start with some sort of input image, some grid of pixels. But rather than immediately put that into the neural network layers that we've seen before, we'll start by applying a convolution step, where the convolution step involves applying some number of different image filters to our original image in order to get what we call a feature map, the result of applying some filter to an image. And we could do this once, but in general, we'll do this multiple times, getting a whole bunch of different feature maps, each of which might extract some different relevant feature out of the image, some different important characteristic of the image that we might care about using in order to calculate what the result should be. And in the same way that when we train neural networks, we can train neural networks to learn the weights between particular units inside of the neural networks. We can also train neural networks to learn what those filters should be, what the values of the filters should be in order to get the most useful, most relevant information out of the original image just by figuring out what setting of those filter values, the values inside of that kernel, results in minimizing the loss function, minimizing how poorly our hypothesis actually performs in figuring out the classification of a particular image, for example. So we first apply this convolution step, get a whole bunch of these various different feature maps. But these feature maps are quite large, right? There's a lot of pixel values that happen to be here. And so a logical next step to take is a pooling step, where we reduce the size of these images by using max pooling, for example, extracting the maximum value from any particular region. There are other pooling methods that exist as well, depending on the situation. You could use something like average pooling, where instead of taking the maximum value from a region, you take the average value from a region, which has its uses as well. But in effect, what pooling will do is it'll take these feature maps and reduce their dimensions so that we end up with smaller grids with fewer pixels. And this then is going to be easier for us to deal with. It's going to mean fewer inputs that we have to worry about. And it's also going to mean we're more resilient, more robust against potential movements of particular values just by one pixel, when ultimately we really don't care about those one pixel differences that might arise in the original image. And now after we've done this pooling step, now we have a whole bunch of values that we can then flatten out and just put into a more traditional neural network. So we go ahead and flatten it, and then we end up with a traditional neural network that has one input for each of these values in each of these resulting feature maps after we do the convolution and after we do the pooling step. And so this then is the general structure of a convolutional network. We begin with the image, apply convolution, apply pooling, flatten the results, and then put that into a more traditional neural network that might itself have hidden layers. You can have deep convolutional networks that have hidden layers in between this flattened layer and the eventual output to be able to calculate various different features of those values. But this then can help us to be able to use convolution and pooling, to use our knowledge about the structure of an image to be able to get better results, to be able to train our networks faster in order to better capture particular parts of the image. And there's no reason necessarily why you can only use these steps once. In fact, in practice, you'll often use convolution and pooling multiple times in multiple different steps. So what you might imagine doing is starting with an image, first applying convolution to get a whole bunch of maps, then applying pooling, then applying convolution again, because these maps are still pretty big. You can apply convolution to try and extract relevant features out of this result. Then take those results, apply pooling in order to reduce their dimensions, and then take that and feed it into a neural network that maybe has fewer inputs. So here I have two different convolution and pooling steps. I do convolution and pooling once, and then I do convolution and pooling a second time, each time extracting useful features from the layer before it, each time using pooling to reduce the dimensions of what you're ultimately looking at. And the goal now of this sort of model is that in each of these steps, you can begin to learn different types of features of the original image. That maybe in the first step, you learn very low-level features. Just learn and look for features like edges and curves and shapes, because based on pixels and their neighboring values, you can figure out, all right, what are the edges, what are the curves, what are the various different shapes that might be present there. But then, once you have a mapping that just represents where the edges and curves and shapes happen to be, you could imagine applying the same sort of process again to begin to look for higher level features, look for objects, maybe look for people's eyes and facial recognition, for example. Maybe look for more complex shapes like the curves on a particular number if you're trying to recognize a digit in a handwriting recognition sort of scenario. And then after all of that, now that you have these results that represent these higher level features, you can pass them into a neural network, which is really just a deep neural network that looks like this, where you might imagine making a binary classification or classifying into multiple categories or performing various different tasks on this sort of model. So convolutional neural networks can be quite powerful and quite popular when it comes towards trying to analyze images. We don't strictly need them. We could have just used a vanilla neural network that just operates with layer after layer, as we've seen before. But these convolutional neural networks can be quite helpful, in particular because of the way they model the way a human might look at an image. That instead of a human looking at every single pixel simultaneously and trying to convolve all of them by multiplying them together, you might imagine that what convolution is really doing is looking at various different regions of the image and extracting relevant information and features out of those parts of the image. The same way that a human might have visual receptors that are looking at particular parts of what they see and using those, combining them to figure out what meaning they can draw from all of those various different inputs. And so you might imagine applying this to a situation like handwriting recognition. So we'll go ahead and see an example of that now, where I'll go ahead and open up handwriting.py. Again, what we do here is we first import TensorFlow. And then TensorFlow, it turns out, has a few data sets that are built into the library that you can just immediately access. And one of the most famous data sets in machine learning is the MNIST data set, which is just a data set of a whole bunch of samples of people's handwritten digits. I showed you a slide of that a little while ago. And what we can do is just immediately access that data set, which is built into the library, so that if I want to do something like train on a whole bunch of handwritten digits, I can just use the data set that is provided to me. Of course, if I had my own data set of handwritten images, I could apply the same idea. I'd first just need to take those images and turn them into like an array of pixels, because that's the way that these are going to be formatted. They're going to be formatted as effectively an array of individual pixels. Now there's a bit of reshaping I need to do, just turning the data into a format that I can put into my convolutional neural network. So this is doing things like taking all the values and dividing them by 255. If you remember, these color values tend to range from 0 to 255. So I can divide them by 255 just to put them into 0 to 1 range, which might be a little bit easier to train on. And then doing various other modifications to the data just to get it into a nice, usable format. But here's the interesting and important part. Here is where I create the convolutional neural network, the CNN, where here I'm saying go ahead and use a sequential model. And before I could use model.add to say add a layer, add a layer, add a layer, another way I could define it is just by passing as input to this sequential neural network a list of all of the layers that I want. And so here, the very first layer in my model is a convolution layer, where I'm first going to apply convolution to my image. I'm going to use 13 different filters. So my model is going to learn 32 different filters that I would like to learn on the input image, where each filter is going to be a 3x3 kernel. So we saw those 3x3 kernels before, where we could multiply each value in a 3x3 grid by a value, multiply and add all the results together. So here I'm going to learn 32 different of these 3x3 filters. I can again specify my activation function, and I specify what my input shape is. My input shape in the banknotes case was just 4. I had 4 inputs. My input shape here is going to be 28, 28, 1, because for each of these handwritten digits, it turns out that the MNIST dataset organizes their data. Each image is a 28 by 28 pixel grid. So we're going to have a 28 by 28 pixel grid. And each one of those images only has one channel value. These handwritten digits are just black and white, so there's just a single color value representing how much black or how much white. You might imagine that in a color image, if you were doing this sort of thing, you might have 3 different channels, a red, a green, and a blue channel, for example. But in the case of just handwriting recognition, recognizing a digit, we're just going to use a single value for like shaded in or not shaded in. And it might range, but it's just a single color value. And that then is the very first layer of our neural network, a convolutional layer that will take the input and learn a whole bunch of different filters that we can apply to the input to extract meaningful features. Next step is going to be a max pooling layer, also built right into TensorFlow, where this is going to be a layer that is going to use a pool size of 2 by 2, meaning we're going to look at 2 by 2 regions inside of the image and just extract the maximum value. Again, we've seen why this can be helpful. It'll help to reduce the size of our input. Once we've done that, we'll go ahead and flatten all of the units just into a single layer that we can then pass into the rest of the neural network. And now, here's the rest of the neural network. Here I'm saying, let's add a hidden layer to my neural network with 128 units, so a whole bunch of hidden units inside of the hidden layer. And just to prevent overfitting, I can add a dropout to that. Say, you know what, when you're training, randomly drop out half of the nodes from this hidden layer, just to make sure we don't become over-reliant on any particular node. We begin to really generalize and stop ourselves from overfitting. So TensorFlow allows us, just by adding a single line, to add dropout into our model as well, such that when it's training, it will perform this dropout step in order to help make sure that we don't overfit on this particular data. And then finally, I add an output layer. The output layer is going to have 10 units, 1 for each category that I would like to classify digits into, so 0 through 9, 10 different categories. And the activation function I'm going to use here is called the softmax activation function. And in short, what the softmax activation function is going to do is it's going to take the output and turn it into a probability distribution. So ultimately, it's going to tell me, like, what did we estimate the probability is that this is a 2 versus a 3 versus a 4. And so it will turn it into that probability distribution for me. Next up, I'll go ahead and compile my model and fit it on all of my training data. And then I can evaluate how well the neural network performs. And then I've added to my Python program, if I've provided a command line argument, like the name of a file, I'm going to go ahead and save the model to a file. And so this can be quite useful too. Once you've done the training step, which could take some time in terms of taking all the time, going through the data, running back propagation with gradient descent to be able to say, all right, how should we adjust the weights of this particular model? You end up calculating values for these weights, calculating values for these filters. You'd like to remember that information so you can use it later. And so TensorFlow allows us to just save a model to a file, such that later, if we want to use the model we've learned, use the weights that we've learned to make some sort of new prediction, we can just use the model that already exists. So what we're doing here is after we've done all the calculation, we go ahead and save the model to a file such that we can use it a little bit later. So for example, if I go into digits, I'm going to run handwriting.py. I won't save it this time. We'll just run it and go ahead and see what happens. What will happen is we need to go through the model in order to train on all of these samples of handwritten digits. So the MNIST dataset gives us thousands and thousands of sample handwritten digits in this same format that we can use in order to train. And so now what you're seeing is this training process. And unlike the banknotes case where there was much fewer data points, the data was very, very simple, here this data is more complex, and this training process takes time. And so this is another one of those cases where when training neural networks, this is why computational power is so important, that oftentimes you see people wanting to use sophisticated GPUs in order to more efficiently be able to do this sort of neural network training. It also speaks to the reason why more data can be helpful. The more sample data points you have, the better you can begin to do this training. So here we're going through 60,000 different samples of handwritten digits. And I said we're going to go through them 10 times. So we're going to go through the data set 10 times, training each time, hopefully improving upon our weights with every time we run through this data set. And we can see over here on the right what the accuracy is each time we go ahead and run this model. That the first time, it looks like we got an accuracy of about 92% of the digits correct based on this training set. We increased that to 96 or 97%. And every time we run this, we're going to see, hopefully, the accuracy improve as we continue to try and use that gradient descent, that process of trying to run the algorithm to minimize the loss that we get in order to more accurately predict what the output should be. And what this process is doing is it's learning not only the weights, but it's learning the features to use, the kernel matrix to use when performing that convolution step, because this is a convolutional neural network, where I'm first performing those convolutions and then doing the more traditional neural network structure. This is going to learn all of those individual steps as well. And so here we see that TensorFlow provides me with some very nice output, telling me about like how many seconds are left with each of these training runs. That allows me to see just how well we're doing. So we'll go ahead and see how this network performs. It looks like we've gone through the data set 7 times. We're going through it an 8th time now. And at this point, the accuracy is pretty high. We went from 92% up to 97%. Now it looks like 98%. And at this point, it seems like things are starting to level out. There's probably a limit to how accurate we can ultimately be without running the risk of overfitting. Of course, with enough nodes, you could just memorize the input and overfit upon them. But we'd like to avoid doing that. And dropout will help us with this. But now we see we're almost done finishing our training step. We're at 55,000. All right, we finished training. And now it's going to go ahead and test for us on 10,000 samples. And it looks like on the testing set, we were 98.8% accurate. So we ended up doing pretty well, it seems, on this testing set to see how accurately can we predict these handwritten digits. And so what we could do then is actually test it out. I've written a program called recognition.py using Pygame. If you pass it a model that's been trained, and I pre-trained an example model using this input data, what we can do is see whether or not we've been able to train this convolutional neural network to be able to predict handwriting, for example. So I can try just like drawing a handwritten digit. I'll go ahead and draw like the number 2, for example. So there's my number 2. Again, this is messy. If you tried to imagine how would you write a program with just like ifs and thens to be able to do this sort of calculation, it would be tricky to do so. But here I'll press classify. And all right, it seems it was able to correctly classify that what I drew was the number 2. I'll go ahead and reset it, try it again. We'll draw like an 8, for example. So here is an 8. I'll press classify. And all right, it predicts that the digit that I drew was an 8. And the key here is this really begins to show the power of what the neural network is doing. Somehow looking at various different features of these different pixels, figuring out what the relevant features are, and figuring out how to combine them to get a classification. And this would be a difficult task to provide explicit instructions to the computer on how to do. Like to use a whole bunch of if-thens to process all of these pixel values to figure out what the handwritten digit is. Like everyone's going to draw their 8s a little bit differently. If I drew the 8 again, it would look a little bit different. And yet ideally, we want to train a network to be robust enough so that it begins to learn these patterns on its own. All I said was here is the structure of the network, and here is the data on which to train the network. And the network learning algorithm just tries to figure out what is the optimal set of weights, what is the optimal set of filters to use in order to be able to accurately classify a digit into one category or another. Just going to show the power of these sorts of convolutional neural networks. And so that then was a look at how we can use convolutional neural networks to begin to solve problems with regards to computer vision, the ability to take an image and begin to analyze it. And so this is the type of analysis you might imagine that's happening in self-driving cars that are able to figure out what filters to apply to an image to understand what it is that the computer is looking at, or the same type of idea that might be applied to facial recognition in social media to be able to determine how to recognize faces in an image as well. You can imagine a neural network that instead of classifying into one of 10 different digits, could instead classify is this person A or is this person B, trying to tell those people apart just based on convolution. And so now what we'll take a look at is yet another type of neural network that can be quite popular for certain types of tasks. But to do so, we'll try to generalize and think about our neural network a little bit more abstractly. That here we have a sampled deep neural network where we have this input layer, a whole bunch of different hidden layers that are performing certain types of calculations, and then an output layer here that just generates some sort of output that we care about calculating. But we could imagine representing this a little more simply like this. Here is just a more abstract representation of our neural network. We have some input that might be like a vector of a whole bunch of different values as our input. That gets passed into a network that performs some sort of calculation or computation, and that network produces some sort of output. That output might be a single value. It might be a whole bunch of different values. But this is the general structure of the neural networks that we've seen. There is some sort of input that gets fed into the network. And using that input, the network calculates what the output should be. And this sort of model for a neural network is what we might call a feed-forward neural network. Feed-forward neural networks have connections only in one direction. They move from one layer to the next layer to the layer after that, such that the inputs pass through various different hidden layers and then ultimately produce some sort of output. So feed-forward neural networks were very helpful for solving these types of classification problems that we saw before. We have a whole bunch of input. We want to learn what setting of weights will allow us to calculate the output effectively. But there are some limitations on feed-forward neural networks that we'll see in a moment. In particular, the input needs to be of a fixed shape, like a fixed number of neurons are in the input layer. And there's a fixed shape for the output, like a fixed number of neurons in the output layer. And that has some limitations of its own. And a possible solution to this, and we'll see examples of the types of problems we can solve with this in just a second, is instead of just a feed-forward neural network, where there are only connections in one direction, from left to right effectively across the network, we could also imagine a recurrent neural network, where a recurrent neural network generates output that gets fed back into itself as input for future runs of that network. So whereas in a traditional neural network, we have inputs that get fed into the network, that get fed into the output, and the only thing that determines the output is based on the original input and based on the calculation we do inside of the network itself. This goes in contrast with a recurrent neural network, where in a recurrent neural network, you can imagine output from the network feeding back to itself into the network again as input for the next time that you do the calculations inside of the network. What this allows is it allows the network to maintain some sort of state, to store some sort of information that can be used on future runs of the network. Previously, the network just defined some weights, and we passed inputs through the network, and it generated outputs. But the network wasn't saving any information based on those inputs to be able to remember for future iterations or for future runs. What a recurrent neural network will let us do is let the network store information that gets passed back in as input to the network again the next time we try and perform some sort of action. And this is particularly helpful when dealing with sequences of data. So we'll see a real-world example of this right now, actually. Microsoft has developed an AI known as the caption bot. And what the caption bot does is it says, I can understand the content of any photograph, and I'll try to describe it as well as any human. I'll analyze your photo, but I won't store it or share it. And so what Microsoft's caption bot seems to be claiming to do is it can take an image and figure out what's in the image and just give us a caption to describe it. So let's try it out. Here, for example, is an image of Harvard Square. It's some people walking in front of one of the buildings at Harvard Square. I'll go ahead and take the URL for that image, and I'll paste it into CaptionBot. And just press Go. So CaptionBot is analyzing the image, and then it says, I think it's a group of people walking in front of a building, which seems amazing. The AI is able to look at this image and figure out what's in the image. And the important thing to recognize here is that this is no longer just a classification task. We saw being able to classify images with a convolutional neural network, where the job was, take the image and then figure out, is it a 0 or a 1 or a 2, or is it this person's face or that person's face? What seems to be happening here is the input is an image, and we know how to get networks to take input as images, but the output is text, like it's a sentence, it's a phrase, like a group of people walking in front of a building. And this would seem to pose a challenge for our more traditional feed-forward neural networks, for the reason being that in traditional neural networks, we just have a fixed size input and a fixed size output. There are a certain number of neurons in the input to our neural network, and a certain number of outputs for our neural network, and then some calculation that goes on in between. But the size of the inputs, the number of values in the input, and the number of values in the output, those are always going to be fixed based on the structure of the neural network. And that makes it difficult to imagine how a neural network could take an image like this and say, it's a group of people walking in front of the building, because the output is text, like it's a sequence of words. Now, it might be possible for a neural network to output like one word. One word you could represent as like a vector of values, and you could imagine ways of doing that. Next time, we'll talk a little bit more about AI as it relates to language and language processing. But a sequence of words is much more challenging, because depending on the image, you might imagine the output is a different number of words. We could have sequences of different lengths, and somehow we still want to be able to generate the appropriate output. And so the strategy here is to use a recurrent neural network, a neural network that can feed its own output back into itself as input for the next time. And this allows us to do what we call a one-to-many relationship for inputs to outputs. That in vanilla, more traditional neural networks, these are what we might consider to be one-to-one neural networks. You pass in one set of values as input, you get one vector of values as the output. But in this case, we want to pass in one value as input, the image, and we want to get a sequence, many values as output, where each value is like one of these words that gets produced by this particular algorithm. And so the way we might do this is we might imagine starting by providing input, the image, into our neural network. And the neural network is going to generate output, but the output is not going to be the whole sequence of words, because we can't represent the whole sequence of words using just a fixed set of neurons. Instead, the output is just going to be the first word. We're going to train the network to output what the first word of the caption should be. And you could imagine that Microsoft has trained this by running a whole bunch of training samples through the AI, giving it a whole bunch of pictures and what the appropriate caption was, and having the AI begin to learn from that. But now, because the network generates output that can be fed back into itself, you could imagine the output of the network being fed back into the same network. This here looks like a separate network, but it's really the same network that's just getting different input. That this network's output gets fed back into itself, but it's going to generate another output. And that other output is going to be like the second word in the caption. And this recurrent neural network then this network is going to generate other output that can be fed back into itself to generate yet another word, fed back into itself to generate another word. And so recurrent neural networks allow us to represent this sort of one-to-many structure. You provide one image as input, and the neural network can pass data into the next run of the network, and then again and again, such that you could run the network multiple times, each time generating a different output, still based on that original input. And this is where recurrent neural networks become particularly useful when dealing with sequences of inputs or outputs. And my output is a sequence of words, and since I can't very easily represent outputting an entire sequence of words, I'll instead output that sequence one word at a time by allowing my network to pass information about what still needs to be said about the photo into the next stage of running the network. So you could run the network multiple times, the same network with the same weights, just getting different input each time. First, getting input from the image, and then getting input from the network itself as additional information about what additionally needs to be given in a particular caption, for example. So this then is a one-to-many relationship inside of a recurrent neural network. But it turns out there are other models that we can use, other ways we can try and use recurrent neural networks to be able to represent data that might be stored in other forms as well. We saw how we could use neural networks in order to analyze images in the context of convolutional neural networks that take an image, figure out various different properties of the image, and are able to draw some sort of conclusion based on that. But you might imagine that something like YouTube, they need to be able to do a lot of learning based on video. They need to look through videos to detect if there are like copyright violations, or they need to be able to look through videos to maybe identify what particular items are inside of the video, for example. And video, you might imagine, is much more difficult to put in as input to a neural network, because whereas an image, you could just treat each pixel as a different value, videos are sequences. They're sequences of images, and each sequence might be of different length. And so it might be challenging to represent that entire video as a single vector of values that you could pass in to a neural network. And so here, too, recurrent neural networks can be a valuable solution for trying to solve this type of problem. That instead of just passing in a single input into our neural network, we could pass in the input like one frame at a time, you might imagine. First, taking the first frame of the video, passing it into the network, and then maybe not having the network output anything at all yet. Let it take in another input, and this time pass it into the network, but the network gets information from the last time we provided an input into the network. Then we pass in a third input and then a fourth input, where each time what the network gets is it gets the most recent input, like each frame of the video, but it also gets information the network processed from all of the previous iterations. So on frame number 4, you end up getting the input for frame number 4, plus information the network has calculated from the first 3 frames. And using all of that data combined, this recurrent neural network can begin to learn how to extract patterns from a sequence of data as well. And so you might imagine if you want to classify a video into a number of different genres, like an educational video or a music video or different types of videos, that's a classification task where you want to take as input each of the frames of the video, and you want to output something like what it is, what category that it happens to belong to. And you can imagine doing this sort of thing, this sort of many-to-one learning, anytime your input is a sequence. And so input is a sequence in the context of video. It could be in the context of like if someone has typed a message and you want to be able to categorize that message. Like if you're trying to take a movie review and trying to classify it as, is it a positive review or a negative review? That input is a sequence of words, and the output is a classification, positive or negative. There, too, a recurrent neural network might be helpful for analyzing sequences of words, and they're quite popular when it comes to dealing with language. Could even be used for spoken language as well. That spoken language is, an audio waveform that can be segmented into distinct chunks, and each of those could be passed in as an input into a recurrent neural network to be able to classify someone's voice, for instance. If you want to do voice recognition to say, is this one person or is this another? Here are also cases where you might want this many-to-one architecture for a recurrent neural network. And then as one final problem, just to take a look at in terms of what we can do with these sorts of networks, imagine what like Google Translate is doing. So what Google Translate is doing is it's taking some text written in one language and converting it into text written in some other language, for example, where now this input is a sequence of data. It's a sequence of words. And the output is a sequence of words as well. It's also a sequence. So here we want effectively like a many-to-many relationship. Our input is a sequence, and our output is a sequence as well. And it's not quite going to work to just say, like, take each word in the input and translate it into a word in the output. Because ultimately, different languages put their words in different orders, and maybe one language uses 2 words for something, whereas another language only uses 1. So we really want some way to take this information, this input, encode it somehow, and use that encoding to generate what the output ultimately should be. And this has been one of the big advancements in automated translation technology, is the ability to use the neural networks to do this instead of older, more traditional methods. And this has improved accuracy dramatically. And the way you might imagine doing this is, again, using a recurrent neural network with multiple inputs and multiple outputs. We start by passing in all the input. Input goes into the network. Another input, like another word, goes into the network. And we do this multiple times, like once for each word in the input that I'm trying to translate. And only after all of that is done does the network now start to generate output, like the first word of the translated sentence, and the next word of the translated sentence, so on and so forth, where each time the network passes information to itself by allowing for this model of giving some sort of state from one run in the network to the next run, assembling information about all the inputs, and then passing in information about which part of the output in order to generate next. And there are a number of different types of these sorts of recurrent neural networks. One of the most popular is known as the long short-term memory neural network, otherwise known as LSTM. But in general, these types of networks can be very, very powerful whenever we're dealing with sequences, whether those are sequences of images or especially sequences of words when it comes towards dealing with natural language. And so that then were just some of the different types of neural networks that can be used to do all sorts of different computations. And these are incredibly versatile tools that can be applied to a number of different domains. We only looked at a couple of the most popular types of neural networks, more traditional feed-forward neural networks, convolutional neural networks, and recurrent neural networks. But there are other types as well. There are adversarial networks, where networks compete with each other to try and be able to generate new types of data, as well as other networks that can solve other tasks based on what they happen to be structured and adapted for. And these are very powerful tools in machine learning for being able to very easily learn based on some set of input data, and to be able to therefore figure out how to calculate some function from inputs to outputs, whether it's input to some sort of classification, like analyzing an image and getting a digit, or machine translation, where the input is in one language and the output is in another. These tools have a lot of applications for machine learning more generally. Next time, we'll look at machine learning and AI in particular in the context of natural language. We talked a little bit about this today, but looking at how it is that our AI can begin to understand natural language and can begin to be able to analyze and do useful tasks with regards to human language, which turns out to be a challenging and interesting task. So we'll see you next time. Welcome back, everybody, to our final class in an introduction to artificial intelligence with Python. Now, so far in this class, we've been taking problems that we want to solve intelligently and framing them in ways that computers are going to be able to make sense of. We've been taking problems and framing them as search problems, or constraint satisfaction problems, or optimization problems, for example. In essence, we have been trying to communicate about problems in ways that our computer is going to be able to understand. Today, the goal is going to be to get computers to understand the way you and I communicate naturally via our own natural languages, languages like English. But natural language contains a lot of nuance and complexity that's going to make it challenging for computers to be able to understand. So we'll need to explore some new tools and some new techniques to allow computers to make sense of natural language. So what is it exactly that we're trying to get computers to do? Well, they all fall under this general heading of natural language processing, getting computers to work with natural language. And these tasks include tasks like automatic summarization. Given a long text, can we train the computer to be able to come up with a shorter representation of it? Information extraction, getting the computer to pull out relevant facts or details out of some text. Machine translation, like Google Translate, translating some text from one language into another language. Question answering, if you've ever asked a question to your phone or had a conversation with an AI chatbot where you provide some text to the computer is able to understand that text and then generate some text in response. Text classification, where we provide some text to the computer, and the computer assigns it a label, positive or negative, inbox or spam, for example. And there are several other kinds of tasks that all fall under this heading of natural language processing. But before we take a look at how the computer might try to solve these kinds of tasks, it might be useful for us to think about language in general. What are the kinds of challenges that we might need to deal with as we start to think about language and getting a computer to be able to understand it? So one part of language that we'll need to consider is the syntax of language. Syntax is all about the structure of language. Language is composed of individual words, and those words are composed together in some kind of structured whole. And if our computer is going to be able to understand language, it's going to need to understand something about that structure. So let's take a couple of examples. Here, for instance, is a sentence. Just before 9 o'clock, Sherlock Holmes stepped briskly into the room. That sentence is made up of words, and those words together form a structured whole. This is syntactically valid as a sentence. But we could take some of those same words, rearrange them, and come up with a sentence that is not syntactically valid. Here, for example, just before Sherlock Holmes 9 o'clock stepped briskly the room is still composed of valid words, but they're not in any kind of logical whole. This is not a syntactically well-formed sentence. Another interesting challenge is that some sentences will have multiple possible valid structures. Here's a sentence, for example. I saw the man on the mountain with a telescope. And here, this is a valid sentence, but it actually has two different possible structures that lend themselves to two different interpretations and two different meanings. Maybe I, the one doing the seeing, am the one with the telescope, or maybe the man on the mountain is the one with the telescope. And so natural language is ambiguous. Sometimes the same sentence can be interpreted in multiple ways, and that's something that we'll need to think about as well. And this lends itself to another problem within language that we'll need to think about, which is semantics. While syntax is all about the structure of language, semantics is about the meaning of language. It's not enough for a computer just to know that a sentence is well structured if it doesn't know what that sentence means. And so semantics is going to concern itself with the meaning of words and the meaning of sentences. So if we go back to that same sentence as before, just before 9 o'clock, Sherlock Holmes stepped briskly into the room, I could come up with another sentence, say the sentence, a few minutes before 9, Sherlock Holmes walked quickly into the room. And those are two different sentences, with some of the words the same and some of the words different. But the two sentences have essentially the same meaning. And so ideally, whatever model we build will be able to understand that these two sentences, while different, mean something very similar. Some syntactically well-formed sentences don't mean anything at all. A famous example from linguist Noam Chomsky is the sentence, colorless green ideas sleep furiously. This is a syntactically, structurally well-formed sentence. We've got adjectives modifying a noun, ideas. We've got a verb and an adverb in the correct positions. But when taken as a whole, the sentence doesn't really mean anything. And so if our computers are going to be able to work with natural language and perform tasks in natural language processing, these are some concerns we'll need to think about. We'll need to be thinking about syntax, and we'll need to be thinking about semantics. So how could we go about trying to teach a computer how to understand the structure of natural language? Well, one approach we might take is by starting by thinking about the rules of natural language. Our natural languages have rules. In English, for example, nouns tend to come before verbs. Nouns can be modified by adjectives, for example. And so if only we could formalize those rules, then we could give those rules to a computer, and the computer would be able to make sense of them and understand them. And so let's try to do exactly that. We're going to try to define a formal grammar, where a formal grammar is some system of rules for generating sentences in a language. This is going to be a rule-based approach to natural language processing. We're going to give the computer some rules that we know about language and have the computer use those rules to make sense of the structure of language. And there are a number of different types of formal grammars. Each one of them has slightly different use cases. But today, we're going to focus specifically on one kind of grammar known as a context-free grammar. So how does a context-free grammar work? Well, here's a sentence that we might want a computer to generate. She saw the city. And we're going to call each of these words a terminal symbol. A terminal symbol because once our computer has generated the word, there's nothing else for it to generate. Once it's generated the sentence, the computer is done. We're going to associate each of these terminal symbols with a non-terminal symbol that generates it. So here we've got N, which stands for noun, like she or city. We've got V as a non-terminal symbol, which stands for a verb. And then we have D, which stands for determiner. A determiner is a word like the or a or an in English, for example. So each of these non-terminal symbols can generate the terminal symbols that we ultimately care about generating. But how do we know, or how does the computer know which non-terminal symbols are associated with which terminal symbols? Well, to do that, we need some kind of rule. Here are some what we call rewriting rules that have a non-terminal symbol on the left-hand side of an arrow. And on the right side is what that non-terminal symbol can be replaced with. So here, we're saying the non-terminal symbol n, again, which stands for noun, could be replaced by any of these options, separated by vertical bars. N could be replaced by she, or city, or car, or Harry. D for determiner could be replaced by the, a, or an, and so forth. Each of these non-terminal symbols could be replaced by any of these words. We can also have non-terminal symbols that are replaced by other non-terminal symbols. Here's an interesting rule. NP arrow n bar dn. So what does that mean? Well, NP stands for a noun phrase. Sometimes when we have a noun phrase in a sentence, it's not just a single word. It could be multiple words. And so here we're saying a noun phrase could be just a noun, or it could be a determiner followed by a noun. So we might have a noun phrase that's just a noun, like she. That's a noun phrase. Or we could have a noun phrase that's multiple words. Something like the city also acts as a noun phrase. But in this case, it's composed of two words, a determiner, the, and a noun, city. We could do the same for verb phrases. A verb phrase, or VP, might be just a verb, or it might be a verb followed by a noun phrase. So we could have a verb phrase that's just a single word, like the word walked, Or we could have a verb phrase that is an entire phrase, something like saw the city as an entire verb phrase. A sentence, meanwhile, we might then define as a noun phrase followed by a verb phrase. And so this would allow us to generate a sentence like, she saw the city, an entire sentence made up of a noun phrase, which is just the word she, and then a verb phrase, which is saw the city, saw, which is a verb, and then the city, which itself is also a noun phrase. And so if we could give these rules to a computer, explaining to it what non-terminal symbols could be replaced by what other symbols, then a computer could take a sentence and begin to understand the structure of that sentence. And so let's take a look at an example of how we might do that. And to do that, we're going to use a Python library called NLTK, or the Natural Language Toolkit, which we'll see a couple of times today. It contains a lot of helpful features and functions that we can use for trying to deal with and process natural language. So here we'll take a look at how we can use NLTK in order to parse a context-free grammar. So let's go ahead and open up cfg0.py, CFG standing for context-free grammar. And what you'll see in this file is that I first import NLTK, the Natural Language Toolkit. And the first thing I do is define a context-free grammar, saying that a sentence is a noun phrase followed by a verb phrase. I'm defining what a noun phrase is, defining what a verb phrase is, and then giving some examples of what I can do with these non-terminal symbols D for determiner, N for noun, and V for verb. We're going to use NLTK to parse that grammar. Then we'll ask the user for some input in the form of a sentence and split it into words. And then we'll use this context-free grammar parser to try to parse that sentence and print out the resulting syntax tree. So let's take a look at an example. I'll go ahead and go into my CFG directory, and we'll run cfg0.py. And here I'm asked to type in a sentence. Let's say I type in she walked. And when I do that, I see that she walked is a valid sentence where she is a noun phrase and walked is the corresponding verb phrase. I could try to do this with a more complex sentence too. I could do something like she saw the city. And here we see that she is the noun phrase, and then saw the city is the entire verb phrase that makes up this sentence. So that was a very simple grammar. Let's take a look at a slightly more complex grammar. Here is cfg1.py, where a sentence is still a noun phrase followed by a verb phrase, but I've added some other possible non-terminal symbols too. I have AP for adjective phrase and PP for prepositional phrase. And we specified that we could have an adjective phrase before a noun phrase, or a prepositional phrase after a noun, for example. So lots of additional ways that we might try to structure a sentence and interpret and parse one of those resulting sentences. So let's see that one in action. We'll go ahead and run cfg1.py with this new grammar. And we'll try a sentence like, she saw the wide street. Here, Python's NLTK is able to parse that sentence and identify that she saw the wide street has this particular structure, a sentence with a noun phrase and a verb phrase, where that verb phrase has a noun phrase that within it contains an adjective. And so it's able to get some sense for what the structure of this language actually is. Let's try another example. Let's say she saw the dog with the binoculars. And we'll try that sentence. And here, we get one possible syntax tree. She saw the dog with the binoculars. But notice that this sentence is actually a little bit ambiguous in our own natural language. Who has the binoculars? Is it she who has the binoculars or the dog who has the binoculars? And NLTK is able to identify both possible structures for the sentence. In this case, the dog with the binoculars is an entire noun phrase. It's all underneath this NP here. So it's the dog that has the binoculars. But we also got an alternative parse tree where the dog is just the noun phrase, and with the binoculars is a prepositional phrase modifying saw. So she saw the dog, and she used the binoculars in order to see the dog as well. So this allows us to get a sense for the structure of natural language, but it relies on us writing all of these rules. And it would take a lot of effort to write all of the rules for any possible sentence that someone might write or say in the English language. Language is complicated, and as a result, there are going to be some very complex rules. So what else might we try? We might try to take a statistical lens towards approaching this problem of natural language processing. If we were able to give the computer a lot of existing data of sentences written in the English language, what could we try to learn from that data? Well, it might be difficult to try and interpret long pieces of text all at once. So instead, what we might want to do is break up that longer text into smaller pieces of information instead. In particular, we might try to create n-grams out of a longer sequence of text. An n-gram is just some contiguous sequence of n items from a sample of text. It might be n characters in a row or n words in a row, for example. So let's take a passage from Sherlock Holmes, and let's look for all of the trigrams. A trigram is an n-gram where n is equal to 3. So in this case, we're looking for sequences of 3 words in a row. So the trigrams here would be phrases like how often have. That's 3 words in a row. Often have I is another trigram. Have I said to you that. These are all trigrams, sequences of 3 words that appear in sequence. And if we could give the computer a large corpus of text and have it pull out all of the trigrams in this case, it could get a sense for what sequences of 3 words tend to appear next to each other in our own natural language, and as a result, get some sense for what the structure of the language actually is. So let's take a look at an example of that. How can we use NLTK to try to get access to information about n-grams? So here, we're going to open up ngrams.py. And this is a Python program that's going to load a corpus of data, just some text files, into our computer's memory. And then we're going to use NLTK's ngrams function, which is going to go through the corpus of text, pulling out all of the n-grams for a particular value of n. And then, by using Python's counter class, we're going to figure out what are the most common n-grams inside of this entire corpus of text. And we're going to need a data set in order to do this. And I've prepared a data set of some of the stories of Sherlock Holmes. So it's just a bunch of text files, a lot of words for it to analyze. And as a result, we'll get a sense for what sequences of 2 words or 3 words tend to be most common in natural language. So let's give this a try. We'll go into my ngrams directory, and we'll run ngrams.py. We'll try an n value of 2. So we're looking for sequences of 2 words in a row. And we'll use our corpus of stories from Sherlock Holmes. And when we run this program, we get a list of the most common n-grams where n is equal to 2, otherwise known as a bigram. So the most common one is of the. That's a sequence of 2 words that appears quite frequently in natural language. Then in the and it was. These are all common sequences of 2 words that appear in a row. Let's instead now try running ngrams with n equal to 3. Let's get all of the trigrams and see what we get. And now we see the most common trigrams are it was a, one of the, I think that. These are all sequences of 3 words that appear quite frequently. And we were able to do this essentially via a process known as tokenization. Tokenization is the process of splitting a sequence of characters into pieces. In this case, we're splitting a long sequence of text into individual words, and then looking at sequences of those words to get a sense for the structure of natural language. So once we've done this, once we've done the tokenization, once we've built up our corpus of n-grams, what can we do with that information? Well, the one thing that we might try is we could build a Markov chain, which you might recall from when we talked about probability. Recall that a Markov chain is some sequence of values where we can predict one value based on the values that came before it. And as a result, if we know all of the common n-grams in the English language, what words tend to be associated with what other words in sequence, we can use that to predict what word might come next in a sequence of words. And so we could build a Markov chain for language in order to try to generate natural language that follows the same statistical patterns as some input data. So let's take a look at that and build a Markov chain for natural language. And as input, I'm going to use the works of William Shakespeare. So here I have a file shakespeare.txt, which is just a bunch of the works of William Shakespeare. It's a long text file, so plenty of data to analyze. And here in generator.py, I'm using a third-party Python library in order to do this analysis. We're going to read in the sample of text, and then we're going to train a Markov model based on that text. And then we're going to have the Markov chain generate some sentences. We're going to generate a sentence that doesn't appear in the original text, but that follows the same statistical patterns, that's generating it based on the n-grams, trying to predict what word is likely to come next that we would expect based on those statistical patterns. So we'll go ahead and go into our Markov directory, run this generator, with the works of William Shakespeare as input. And what we're going to get are 5 new sentences where these sentences are not necessarily sentences from the original input text itself, but just that follow the same statistical patterns. It's predicting what word is likely to come next based on the input data that we've seen and the types of words that tend to appear in sequence there too. And so we're able to generate these sentences. Of course, so far, there's no guarantee that any of the sentences that are generated actually mean anything or make any sense. They just happen to follow the statistical patterns that our computer is already aware of. So we'll return to this issue of how to generate text in perhaps a more accurate or more meaningful way a little bit later. So let's now turn our attention to a slightly different problem, and that's the problem of text classification. Text classification is the problem where we have some text, and we want to put that text into some kind of category. We want to apply some sort of label to that text. And this kind of problem shows up in a wide variety of places. A common place might be your email inbox, for example. You get an email, and you want your computer to be able to identify whether the email belongs in your inbox or whether it should be filtered out into spam. So we need to classify the text. Is it a good email, or is it spam? Another common use case is sentiment analysis. We might want to know whether the sentiment of some text is positive or negative. And so how might we do that? This comes up in situations like product reviews, where we might have a bunch of reviews for a product on some website. My grandson loved it, so much fun. Product broke after a few days. One of the best games I've played in a long time, and kind of cheap and flimsy, not worth it. Here's some example sentences that you might see on a product review website. And you and I could pretty easily look at this list of product reviews and decide which ones are positive and which ones are negative. We might say the first one and the third one, those seem like positive sentiment messages, but the second one and the fourth one seem like negative sentiment messages. But how did we know that? And how could we train a computer to be able to figure that out as well? Well, you might have clued your eye in on particular keywords, where those particular words tend to mean something positive or negative. So you might have identified words like loved and fun and best tend to be associated with positive messages, and words like broke and cheap and flimsy tend to be associated with negative messages. So if only we could train a computer to be able to learn what words tend to be associated with positive versus negative messages, then maybe we could train a computer to do this kind of sentiment analysis as well. So we're going to try to do just that. We're going to use a model known as the bag of words model, which is a model that represents text as just an unordered collection of words. For the purpose of this model, we're not going to worry about the sequence and the ordering of the words, which word came first, second, or third. We're just going to treat the text as a collection of words in no particular order. And we're losing information there, right? The order of words is important, and we'll come back to that a little bit later. But for now, to simplify our model, it'll help us tremendously just to think about text as some unordered collection of words. And in particular, we're going to use the bag of words model to build something known as a naive Bayes classifier. So what is a naive Bayes classifier? Well, it's a tool that's going to allow us to classify text based on Bayes' rule, again, which you might remember from when we talked about probability. Bayes' rule says that the probability of B given A is equal to the probability of A given B multiplied by the probability of B divided by the probability of A. So how are we going to use this rule to be able to analyze text? Well, what are we interested in? We're interested in the probability that a message has a positive sentiment and the probability that a message has a negative sentiment, which I'm here for simplicity going to represent just with these emoji, happy face and frown face, as positive and negative sentiment. And so if I had a review, something like my grandson loved it, then what I'm interested in is not just the probability that a message has positive sentiment, but the conditional probability that a message has positive sentiment given that this is the message, my grandson loved it. But how do I go about calculating this value, the probability that the message is positive, given that the review is this sequence of words? Well, here's where the bag of words model comes in. Rather than treat this review as a string of a sequence of words in order, we're just going to treat it as an unordered collection of words. We're going to try to calculate the probability that the review is positive, given that all of these words, my grandson loved it, are in the review in no particular order, just this unordered collection of words. And this is a conditional probability, which we can then apply Bayes' rule to try to make sense of. So according to Bayes' rule, this conditional probability is equal to what? It's equal to the probability that all of these 4 words are in the review, given that the review is positive, multiplied by the probability that the review is positive, divided by the probability that all of these words happen to be in the review. So this is the value now that we're going to try to calculate. Now, one thing you might notice is that the denominator here, the probability that all of these words appear in the review, doesn't actually depend on whether or not we're looking at the positive sentiment or negative sentiment case. So we can actually get rid of this denominator. We don't need to calculate it. We can just say that this probability is proportional to the numerator. And then at the end, we're going to need to normalize the probability distribution to make sure that all of the values sum up to the value 1. So now, how do we calculate this value? Well, this is the probability of all of these words given positive times probability of positive. And that, by the definition of joint probability, is just one big joint probability, the probability that all of these things are the case, that it's a positive review and that all 4 of these words are in the review. But still, it's not entirely obvious how we calculate that value. And here's where we need to make one more assumption. And this is where the naive part of naive Bayes comes in. We're going to make the assumption that all of the words are independent of each other. And by that, I mean that if the word grandson is in the review, that doesn't change the probability that the word loved is in the review, or that the word it is in the review, for example. And in practice, this assumption might not be true. It's almost certainly the case that the probability of words do depend on each other. But it's going to simplify our analysis and still give us reasonably good results, just to assume that the words are independent of each other, and they only depend on whether it's positive or negative. You might, for example, expect the word loved to appear more often in a positive review than in a negative review. So what does that mean? Well, if we make this assumption, then we can say that this value, the probability we're interested in, is not directly proportional to, but it's naively proportional to this value. The probability that the review is positive times the probability that my is in the review, given that it's positive, times the probability that grandson is in the review, given that it's positive, and so on for the other 2 words that happen to be in this review. And now this value, which looks a little more complex, is actually a value that we can calculate pretty easily. So how are we going to estimate the probability that the review is positive? Well, if we have some training data, some example data of example reviews where each one has already been labeled as positive or negative, then we can estimate the probability that a review is positive just by counting the number of positive samples and dividing by the total number of samples that we have in our training data. And for the conditional probabilities, the probability of loved, given that it's positive, well, that's going to be the number of positive samples with loved in it divided by the total number of positive samples. So let's take a look at an actual example to see how we could try to calculate these values. Here I've put together some sample data. The way to interpret the sample data is that based on the training data, 49% of the reviews are positive, 51% are negative. And then over here in this table, we have some conditional probabilities. We have, if the review is positive, then there's a 30% chance that my appears in it. And if the review is negative, there's a 20% chance that my appears in it. And based on our training data, among the positive reviews, 1% of them contain the word grandson. And among the negative reviews, 2% contain the word grandson. So using this data, let's try to calculate this value, the value we're interested in. And to do that, we'll need to multiply all of these values together. The probability of positive, and then all of these positive conditional probabilities. And when we do that, we get some value. And then we can do the same thing for the negative case. We're going to do the same thing, take the probability that it's negative, multiply it by all of these conditional probabilities, and we're going to get some other value. And now these values don't sum to 1. They're not a probability distribution yet. But I can normalize them and get some values. And that tells me that we're going to predict that my grandson loved it. We think there's a 68% chance, probability 0.68, that that is a positive sentiment review, and 0.32 probability that it's a negative review. So what problems might we run into here? What could potentially go wrong when doing this kind of analysis in order to analyze whether text has a positive or negative sentiment? Well, a couple of problems might arise. One problem might be, what if the word grandson never appears for any of the positive reviews? If that were the case, then when we try to calculate the value, the probability that we think the review is positive, we're going to multiply all these values together, and we're just going to get 0 for the positive case, because we're going to ultimately multiply by that 0 value. And so we're going to say that we think there's no chance that the review is positive because it contains the word grandson. And in our training data, we've never seen the word grandson appear in a positive sentiment message before. And that's probably not the right analysis, because in cases of rare words, it might be the case that nowhere in our training data did we ever see the word grandson appear in a message that has positive sentiment. So what can we do to solve this problem? Well, one thing we'll often do is some kind of additive smoothing, where we add some value alpha to each value in our distribution just to smooth out the data a little bit. And a common form of this is Laplace smoothing, where we add 1 to each value in our distribution. In essence, we pretend we've seen each value one more time than we actually have. If we've never seen the word grandson for a positive review, we pretend we've seen it once. If we've seen it once, we pretend we've seen it twice, just to avoid the possibility that we might multiply by 0, and as a result, get some results we don't want in our analysis. So let's see what this looks like in practice. Let's try to do some naive Bayes classification in order to classify text as either positive or negative. We'll take a look at sentiment.py. And what this is going to do is load some sample data into memory, some examples of positive reviews and negative reviews. And then we're going to train a naive Bayes classifier on all of this training data. Training data that includes all of the words we see in positive reviews and all of the words we see in negative reviews. And then we're going to try to classify some input. And so we're going to do this based on a corpus of data. I have some example positive reviews. Here's some positive reviews. It was great, so much fun, for example. And then some negative reviews. Not worth it, kind of cheap. These are some examples of negative reviews. So now let's try to run this classifier and see how it would classify particular text as either positive or negative. We'll go ahead and run our sentiment analysis on this corpus. And we need to provide it with a review. So I'll say something like, I enjoyed it. And we see that the classifier says there's about a 0.92 probability that we think that this particular review is positive. Let's try something negative. We'll try kind of overpriced. And we see that there is a 0.96 probability now that we think that this particular review is negative. And so our naive Bayes classifier has learned what kinds of words tend to appear in positive reviews and what kinds of words tend to appear in negative reviews. And as a result of that, we've been able to design a classifier that can predict whether a particular review is positive or negative. And so this definitely is a useful tool that we can use to try and make some predictions. But we had to make some assumptions in order to get there. So what if we want to now try to build some more sophisticated models, use some tools from machine learning to try and take better advantage of language data to be able to draw more accurate conclusions and solve new kinds of tasks and new kinds of problems? Well, we've seen a couple of times now that when we want to take some data and take some input, put it in a way that the computer is going to be able to make sense of, it can be helpful to take that data and turn it into numbers ultimately. And so what we might want to try to do is come up with some word representation, some way to take a word and translate its meaning into numbers. Because, for example, if we wanted to use a neural network to be able to process language, give our language to a neural network and have it make some predictions or perform some analysis there, a neural network takes as input and produces as output a vector of values, a vector of numbers. And so what we might want to do is take our data and somehow take words and convert them into some kind of numeric representation. So how might we do that? How might we take words and turn them into numbers? Let's take a look at an example. Here's a sentence, he wrote a book. And let's say I wanted to take each of those words and turn it into a vector of values. Here's one way I might do that. We'll say he is going to be a vector that has a 1 in the first position, and the rest of the values are 0. Wrote will have a 1 in the second position, and the rest of the values are 0. A has a 1 in the third position, with the rest of the values 0. And book has a 1 in the fourth position, with the rest of the values 0. So each of these words now has a distinct vector representation. And this is what we often call a one-hot representation, a representation of the meaning of a word as a vector with a single 1, and all of the rest of the values are 0. And so when doing this, we now have a numeric representation for every word. And we could pass in those vector representations into a neural network or other models that require some kind of numeric data as input. But this one-hot representation actually has a couple of problems, and it's not ideal for a few reasons. One reason is, here we're just looking at 4 words. But if you imagine a vocabulary of thousands of words or more, these vectors are going to get quite long in order to have a distinct vector for every possible word in a vocabulary. And as a result of that, these longer vectors are going to be more difficult to deal with, more difficult to train, and so forth. And so that might be a problem. Another problem is a little bit more subtle. If we want to represent a word as a vector, and in particular the meaning of a word as a vector, then ideally it should be the case that words that have similar meanings should also have similar vector representations, so that they're close to each other together inside of vector space. But that's not really going to be the case with these one-hot representations, because if we take some similar words, say the word wrote and the word authored, which mean similar things, they have entirely different vector representations. Likewise, book and novel, those 2 words mean somewhat similar things, but they have entirely different vector representations because they each have a 1 in some different position. And so that's not ideal either. So what we might be interested in instead is some kind of distributed representation. A distributed representation is the representation of the meaning of a word distributed across multiple values, instead of just being one-hot with a 1 in one position. Here is what a distributed representation of words might be. Each word is associated with some vector of values with the meaning distributed across multiple values, ideally in such a way that similar words have a similar vector representation. But how are we going to come up with those values? Where do those values come from? How can we define the meaning of a word in this distributed sequence of numbers? Well, to do that, we're going to draw inspiration from a quote from British linguist J.R. Firth, who said, "You shall know a word by the company it keeps." In other words, we're going to define the meaning of a word based on the words that appear around it, the context words around it. Take, for example, this context. For blank he ate. You might wonder what words could reasonably fill in that blank. Well, it might be words like breakfast, or lunch, or dinner. All of those could reasonably fill in that blank. And so what we're going to say is, because the words breakfast and lunch and dinner appear in a similar context, that they must have a similar meaning. And that's something our computer could understand and try to learn. A computer could look at a big corpus of text, look at what words tend to appear in similar context to each other, and use that to identify which words have a similar meaning and should therefore appear close to each other inside of vector space. And so one common model for doing this is known as the word-to-vec model. It's a model for generating word vectors, a vector representation for every word, by looking at data and looking at the context in which a word appears. The idea is going to be this. If you start out with all of the words just in some random position in space and train it on some training data, what the word-to-vec model will do is start to learn what words appear in similar contexts, and it will move these vectors around in such a way that hopefully words with similar meanings, breakfast, lunch, and dinner, book, memoir, novel, will hopefully appear to be near to each other as vectors as well. So let's now take a look at what word-to-vec might look like in practice when implemented in code. What I have here inside of words.txt is a pre-trained model where each of these words has some vector representation trained by word-to-vec. Each of these words has some sequence of values representing its meaning, hopefully in such a way that similar words are represented by similar vectors. I also have this file vectors.py, which is going to open up the words and form them into a dictionary. And we also define some useful functions like distance to get the distance between 2 word vectors, and closest words to find which words are nearby in terms of having close vectors to each other. And so let's give this a try. We'll go ahead and open a Python interpreter. And I'm going to import these vectors. And we might say, all right, what is the vector representation of the word book? And we get this big, long vector that represents the word book as a sequence of values. And this sequence of values by itself is not all that meaningful, but it is meaningful in the context of comparing it to other vectors for other words. So we could use this distance function, which is going to get us the distance between 2 word vectors. And we might say, what is the distance between the vector representation for the word book and the vector representation for the word novel? And we see that it's 0.34. You can kind of interpret 0 as being really close together and 1 being very far apart. And so now, what is the distance between book and, let's say, breakfast? Well, book and breakfast are more different from each other than book and novel are, so I would hopefully expect the distance to be larger. And in fact, it is, 0.64 approximately. These two words are further away from each other. And what about now the distance between, let's say, lunch and breakfast? Well, that's about 0.2. Those are even closer together. They have a meaning that is closer to each other. Another interesting thing we might do is calculate the closest words. We might say, what are the closest words, according to word2vec, to the word book? And let's get the 10 closest words. What are the 10 closest vectors to the vector representation for the word book? And when we perform that analysis, we get this list of words. The closest one is book itself, but we also have books plural, and then essay, memoir, essays, novella, anthology, and so on. All of these words mean something similar to the word book, according to word2vec at least, because they have a similar vector representation. So it seems like we've done a pretty good job of trying to capture this kind of vector representation of word meaning. One other interesting side effect of word2vec is that it's also able to capture something about the relationships between words as well. Let's take a look at an example. Here, for instance, are two words, man and king, and these are each represented by word2vec as vectors. So what might happen if I subtracted one from the other, calculated the value king minus man? Well, that will be the vector that will take us from man to king, somehow represent this relationship between the vector representation of the word man and the vector representation of the word king. And that's what this value, king minus man, represents. So what would happen if I took the vector representation of the word woman and added that same value, king minus man, to it? What would we get as the closest word to that, for example? Well, we could try it. Let's go ahead and go back to our Python interpreter and give this a try. I could say, what is the closest word to the vector representation of the word king minus the representation of the word man plus the representation of the word woman? And we see that the closest word is the word queen. We've somehow been able to capture the relationship between king and man. And then when we apply it to the word woman, we get, as the result, the word queen. So word2vec has been able to capture not just the words and how they're similar to each other, but also something about the relationships between words and how those words are connected to each other. So now that we have this vector representation of words, what can we now do with it? Now we can represent words as numbers. And so we might try to pass those words as input to, say, a neural network. Neural networks, we've seen, are very powerful tools for identifying patterns and making predictions. Recall that a neural network you can think of as all of these units. But really what the neural network is doing is taking some input, passing it into the network, and then producing some output. And by providing the neural network with training data, we're able to update the weights inside of the network so that the neural network can do a more accurate job of translating those inputs into those outputs. And now that we can represent words as numbers that could be the input or output, you could imagine passing a word in as input to a neural network and getting a word as output. And so when might that be useful? One common use for neural networks is in machine translation, when we want to translate text from one language into another, say translate English into French, by passing English into the neural network and getting some French output. You might imagine, for instance, that we could take the English word for lamp, pass it into the neural network, get the French word for lamp as output. But in practice, when we're translating text from one language to another, we're usually not just interested in translating a single word from one language to another, but a sequence, say a sentence or a paragraph of words. Here, for example, is another paragraph, again taken from Sherlock Holmes, written in English. And what I might want to do is take that entire sentence, pass it into the neural network, and get as output a French translation of the same sentence. But recall that a neural network's input and output needs to be of some fixed size. And a sentence is not a fixed size. It's variable. You might have shorter sentences, and you might have longer sentences. So somehow we need to solve the problem of translating a sequence into another sequence by means of a neural network. And that's going to be true not only for machine translation, but also for other problems. Problems like question answering. If I want to pass as input a question, something like, what is the capital of Massachusetts, feed that as input into the neural network, I would hope that what I would get as output is a sentence like, the capital is Boston. Again, translating some sequence into some other sequence. And if you've ever had a conversation with an AI chatbot or have ever asked your phone a question, it needs to do something like this. It needs to understand the sequence of words that you, the human, provided as input. And then the computer needs to generate some sequence of words as output. So how can we do this? Well, one tool that we can use is the recurrent neural network, which we took a look at last time, which is a way for us to provide a sequence of values to a neural network by running the neural network multiple times. And each time we run the neural network, what we're going to do is we're going to keep track of some hidden state. And that hidden state is going to be passed from one run of the neural network to the next run of the neural network, keeping track of all of the relevant information. And so let's take a look at how we could apply that to something like this. And in particular, we're going to look at an architecture known as an encoder-decoder architecture, where we're going to encode this question into some kind of hidden state, and then use a decoder to decode that hidden state into the output that we're interested in. So what's that going to look like? We'll start with the first word, the word what. That goes into our neural network, and it's going to produce some hidden state. This is some information about the word what that our neural network is going to need to keep track of. Then when the second word comes along, we're going to feed it into that same encoder neural network, but it's going to get as input that hidden state as well. So we pass in the second word. We also get the information about the hidden state. And that's going to continue for the other words in the input. This is going to produce a new hidden state. And so then when we get to the third word, the, that goes into the encoder. It also gets access to the hidden state. And then it produces a new hidden state that gets passed into the next run when we use the word capital. And the same thing is going to repeat for the other words that appear in the input. So of Massachusetts, that produces one final piece of hidden state. Now somehow we need to signal the fact that we're done. There's nothing left in the input. And we typically do this by passing some kind of special token, say an end token, into the neural network. And now the decoding process is going to start. We're going to generate the word the. But in addition to generating the word the, this decoder network is also going to generate some kind of hidden state. And so what happens the next time? Well, to generate the next word, it might be helpful to know what the first word was. So we might pass the first word, the, back into the decoder network. It's going to get as input this hidden state, and it's going to generate the next word, capital. And that's also going to generate some hidden state. And we'll repeat that, passing capital into the network to generate the third word, is, and then one more time in order to get the fourth word, Boston. And at that point, we're done. But how do we know we're done? Usually, we'll do this one more time, pass Boston into the decoder network, and get as output some end token to indicate that that is the end of our input. And so this then is how we could use a recurrent neural network to take some input, encode it into some hidden state, and then use that hidden state to decode it into the output we're interested in. To visualize it in a slightly different way, we have some input sequence. This is just some sequence of words. That input sequence goes into the encoder, which in this case is a recurrent neural network generating these hidden states along the way until we generate some final hidden state, at which point we start the decoding process. Again, using a recurrent neural network, that's going to generate the output sequence as well. So we've got the encoder, which is encoding the information about the input sequence into this hidden state, and then the decoder, which takes that hidden state and uses it in order to generate the output sequence. But there are some problems. And for many years, this was the state of the art. The recurrent neural network and variants on this approach were some of the best ways we knew in order to perform tasks in natural language processing. But there are some problems that we might want to try to deal with and that have been dealt with over the years to try and improve upon this kind of model. And one problem you might notice happens in this encoder stage. We've taken this input sequence, the sequence of words, and encoded it all into this final piece of hidden state. And that final piece of hidden state needs to contain all of the information from the input sequence that we need in order to generate the output sequence. And while that's possible, it becomes increasingly difficult as the sequence gets larger and larger. For larger and larger input sequences, it's going to become more and more difficult to store all of the information we need about the input inside this single hidden state piece of context. That's a lot of information to pack into just a single value. It might be useful for us when generating output to not just refer to this one value, but to all of the previous hidden values that have been generated by the encoder. And so that might be useful. But how could we do that? We've got a lot of different values. We need to combine them somehow. So you could imagine adding them together, taking the average of them, for example. But doing that would assume that all of these pieces of hidden state are equally important. But that's not necessarily true either. Some of these pieces of hidden state are going to be more important than others, depending on what word they most closely correspond to. This piece of hidden state very closely corresponds to the first word of the input sequence. This one very closely corresponds to the second word of the input sequence, for example. And some of those are going to be more important than others. To make matters more complicated, depending on which word of the output sequence we're generating, different input words might be more or less important. And so what we really want is some way to decide for ourselves which of the input values are worth paying attention to at what point in time. And this is the key idea behind a mechanism known as attention. Attention is all about letting us decide which values are important to pay attention to when generating, in this case, the next word in our sequence. So let's take a look at an example of that. Here's a sentence. What is the capital of Massachusetts? Same sentence as before. And let's imagine that we were trying to answer that question by generating tokens of output. So what would the output look like? Well, it's going to look like something like the capital is. And let's say we're now trying to generate this last word here. What is that last word? How is the computer going to figure it out? Well, what it's going to need to do is decide which values it's going to pay attention to. And so the attention mechanism will allow us to calculate some attention scores for each word, some value corresponding to each word, determining how relevant is it for us to pay attention to that word right now. And in this case, when generating the fourth word of the output sequence, the most important words to pay attention to might be capital and Massachusetts, for example. That those words are going to be particularly relevant. And there are a number of different mechanisms that have been used in order to calculate these attention scores. It could be something as simple as a dot product to see how similar two vectors are, or we could train an entire neural network to calculate these attention scores. But the key idea is that during the training process for our neural network, we're going to learn how to calculate these attention scores. Our model is going to learn what is important to pay attention to in order to decide what the next word should be. So the result of all of this, calculating these attention scores, is that we can calculate some value for each input word, determining how important is it for us to pay attention to that particular value. And recall that each of these input words is also associated with one of these hidden state context vectors, capturing information about the sentence up to that point, but primarily focused on that word in particular. And so what we can now do is if we have all of these vectors and we have values representing how important is it for us to pay attention to those particular vectors, is we can take a weighted average. We can take all of these vectors, multiply them by their attention scores, and add them up to get some new vector value, which is going to represent the context from the input, but specifically paying attention to the words that we think are most important. And once we've done that, that context vector can be fed into our decoder in order to say that the word should be, in this case, Boston. So attention is this very powerful tool that allows any word, when we're trying to decode it, to decide which words from the input should we pay attention to in order to determine what's important for generating the next word of the output. And one of the first places this was really used was in the field of machine translation. Here's an example of a diagram from the paper that introduced this idea, which was focused on trying to translate English sentences into French sentences. So we have an input English sentence up along the top, and then along the left side, the output French equivalent of that same sentence. And what you see in all of these squares are the attention scores visualized, where a lighter square indicates a higher attention score. And what you'll notice is that there's a strong correspondence between the French word and the equivalent English word, that the French word for agreement is really paying attention to the English word for agreement in order to decide what French word should be generated at that point in time. And sometimes you might pay attention to multiple words. If you look at the French word for economic, that's primarily paying attention to the English word for economic, but also paying attention to the English word for European in this case too. And so attention scores are very easy to visualize to get a sense for what is our machine learning model really paying attention to? What information is it using in order to determine what's important and what's not, in order to determine what the ultimate output token should be? And so when we combine the attention mechanism with a recurrent neural network, we can get very powerful and useful results where we're able to generate an output sequence by paying attention to the input sequence too. But there are other problems with this approach of using a recurrent neural network as well. In particular, notice that every run of the neural network depends on the output of the previous step. And that was important for getting a sense for the sequence of words and the ordering of those particular words. But we can't run this unit of the neural network until after we've calculated the hidden state from the run before it, from the previous input token. And what that means is that it's very difficult to parallelize this process. That as the input sequence gets longer and longer, we might want to use parallelism to try and speed up this process of training the neural network and making sense of all of this language data. But it's difficult to do that, and it's slow to do that with a recurrent neural network because all of it needs to be performed in sequence. And that's become an increasing challenge as we've started to get larger and larger language models. The more language data that we have available to us to use to train our machine learning models, the more accurate it can be, the better representation of language it can have, the better understanding it can have, and the better results that we can see. And so we've seen this growth of large language models that are using larger and larger data sets, but as a result, they take longer and longer to train. And so this problem that recurrent neural networks are not easy to parallelize has become an increasing problem. And as a result of that, that was one of the main motivations for a different architecture for thinking about how to deal with natural language, and that's known as the transformer architecture. And this has been a significant milestone in the world of natural language processing for really increasing how well we can perform these kinds of natural language processing tasks, as well as how quickly we can train a machine learning model to be able to produce effective results. There are a number of different types of transformers in terms of how they work, but what we're going to take a look at here is the basic architecture for how one might work with a transformer to get a sense for what's involved and what we're doing. So let's start with the model we were looking at before, specifically at this encoder part of our encoder-decoder architecture, where we used a recurrent neural network to take this input sequence and capture all of this information about the hidden state and the information we need to know about that input sequence. Right now, it all needs to happen in this linear progression. But what the transformer is going to allow us to do is process each of the words independently in a way that's easy to parallelize. Rather than have each word wait for some other word, each word is going to go through this same neural network and produce some kind of encoded representation of that particular input word. And all of this is going to happen in parallel. Now, it's happening for all of the words at once, but we're really just going to focus on what's happening for one word to make it clear. But know that whatever you're seeing happen for this one word is going to happen for all of the other input words too. So what's going on here? Well, we start with some input word. That input word goes into the neural network, and the output is hopefully some encoded representation of the input word, the information we need to know about the input word that's going to be relevant to us as we're generating the output. And because we're doing this each word independently, it's easy to parallelize. We don't have to wait for the previous word before we run this word through the neural network. But what did we lose in this process by trying to parallelize this whole thing? Well, we've lost all notion of word ordering. The order of words is important. The sentence, Sherlock Holmes gave the book to Watson, has a different meaning than Watson gave the book to Sherlock Holmes. And so we want to keep track of that information about word position. In the recurrent neural network, that happened for us automatically because we could run each word one at a time through the neural network, get the hidden state, pass it on to the next run of the neural network. But that's not the case here with the transformer, where each word is being processed independent of all of the other ones. So what are we going to do to try to solve that problem? One thing we can do is add some kind of positional encoding to the input word. The positional encoding is some vector that represents the position of the word in the sentence. This is the first word, the second word, the third word, and so forth. We're going to add that to the input word. And the result of that is going to be a vector that captures multiple pieces of information. It captures the input word itself, as well as where in the sentence it appears. The result of that is we can pass the output of that addition, the addition of the input word and the positional encoding, into the neural network. That way the neural network knows the word and where it appears in the sentence and can use both of those pieces of information to determine how best to represent the meaning of that word in the encoded representation at the end of it. In addition to what we have here, in addition to the positional encoding and this feed-forward neural network, we're also going to add one additional component, which is going to be a self-attention step. This is going to be attention where we're paying attention to the other input words, because the meaning or interpretation of an input word might vary depending on the other words in the input as well. And so we're going to allow each word in the input to decide what other words in the input it should pay attention to in order to decide on its encoded representation. And that's going to allow us to get a better encoded representation for each word, because words are defined by their context, by the words around them and how they're used in that particular context. This kind of self-attention is so valuable, in fact, that oftentimes the transformer will use multiple different self-attention layers at the same time to allow for this model to be able to pay attention to multiple facets of the input at the same time. We call this multi-headed attention, where each attention head can pay attention to something different. And as a result, this network can learn to pay attention to many different parts of the input for this input word all at the same time. And in the spirit of deep learning, these two steps, this multi-headed self-attention layer and this neural network layer, that itself can be repeated multiple times too, in order to get a deeper representation, in order to learn deeper patterns within the input text, and ultimately get a better representation of language in order to get useful encoded representations of all of the input words. And so this is the process that a transformer might use in order to take an input word and get it its encoded representation. And the key idea is to really rely on this attention step in order to get information that's useful in order to determine how to encode that word. And that process is going to repeat for all of the input words that are in the input sequence. We're going to take all of the input words, encode them with some kind of positional encoding, feed those into these self-attention and feed-forward neural networks in order to ultimately get these encoded representations of the words. That's the result of the encoder. We get all of these encoded representations that will be useful to us when it comes time then to try to decode all of this information into the output sequence we're interested in. And again, this might take place in the context of machine translation, where the output is going to be the same sentence in a different language, or it might be an answer to a question in the case of an AI chatbot, for example. And so now let's take a look at how that decoder is going to work. Ultimately, it's going to have a very similar structure. Anytime we're trying to generate the next output word, we need to know what the previous output word is, as well as its positional encoding. Where in the output sequence are we? And we're going to have these same steps. Self-attention, because we might want an output word to be able to pay attention to other words in that same output, as well as a neural network. And that might itself repeat multiple times. But in this decoder, we're going to add one additional step. We're going to add an additional attention step, where instead of self-attention, where the output word is going to pay attention to other output words, in this step, we're going to allow the output word to pay attention to the encoded representations. So recall that the encoder is taking all of the input words and transforming them into these encoded representations of all of the input words. But it's going to be important for us to be able to decide which of those encoded representations we want to pay attention to when generating any particular token in the output sequence. And that's what this additional attention step is going to allow us to do. It's saying that every time we're generating a word of the output, we can pay attention to the other words in the output, because we might want to know what are the words we've generated previously, and we want to pay attention to some of them to decide what word is going to be next in the sequence. But we also care about paying attention to the input words too. And we want the ability to decide which of these encoded representations of the input words are going to be relevant in order for us to generate the next step. And so these two pieces combine together. We have this encoder that takes all of the input words and produces this encoded representation. And we have this decoder that is able to take the previous output word, pay attention to that encoded input, and then generate the next output word And this is one of the possible architectures we could use for a transformer, with the key idea being these attention steps that allow words to pay attention to each other. During the training process here, we can now much more easily parallelize this, because we don't have to wait for all of the words to happen in sequence. And we can learn how we should perform these attention steps. The model is able to learn what is important to pay attention to, what things do I need to pay attention to in order to be more accurate at predicting what the output word is. And this has proved to be a tremendously effective model for conversational AI agents, for building machine translation systems. And there have been many variants proposed on this model, too. Some transformers only use an encoder. Some only use a decoder. Some use some other combination of these different particular features. But the key ideas ultimately remain the same, this real focus on trying to pay attention to what is most important. And the world of natural language processing is fast growing and fast evolving. Year after year, we keep coming up with new models that allow us to do an even better job of performing these natural language related tasks, all on the surface of solving the tricky problem, which is our own natural language. We've seen how the syntax and semantics of our language is ambiguous, and it introduces all of these new challenges that we need to think about if we're going to be able to design AI agents that are able to work with language effectively. So as we think about where we've been in this class, all of the different types of artificial intelligence we've considered, we've looked at artificial intelligence in a wide variety of different forms now. We started by taking a look at search problems, where we looked at how AI can search for solutions, play games, and find the optimal decision to make. We talked about knowledge, how AI can represent information that it knows and use that information to generate new knowledge as well. Then we looked at what AI can do when it's less certain, when it doesn't know things for sure, and we have to represent things in terms of probability. We then took a look at optimization problems. We saw how a lot of problems in AI can be boiled down to trying to maximize or minimize some function. And we looked at strategies that AI can use in order to do that kind of maximizing and minimizing. We then looked at the world of machine learning from data in order to figure out some patterns and identify how to perform a task by looking at the training data that we have available to it. And one of the most powerful tools there was the neural network, the sequence of units whose weights can be trained in order to allow us to really effectively go from input to output and predict how to get there by learning these underlying patterns. And then today, we took a look at language itself, trying to understand how can we train the computer to be able to understand our natural language, to be able to understand syntax and semantics, make sense of and generate natural language, which introduces a number of interesting problems too. And we've really just scratched the surface of artificial intelligence. There's so much interesting research and interesting new techniques and algorithms and ideas being introduced to try to solve these types of problems. So I hope you enjoyed this exploration into the world of artificial intelligence. A huge thanks to all of the course's teaching staff and production team for making the class possible. This was an introduction to artificial intelligence with Python.